propel the vehicle. And our vehicle is obviously the aircraft, all right? And it will be attached to some sort of shaft and a decent type engine, which will have several blades, okay, attached to it. And as I say, we can thrust the boat through the water using propeller, or we can thrust the aircraft, the vehicle, through the air. Okay. Again, various types of sizes, some quite small ones to some quite large ones, but the principle is exactly the same, just using a different medium. Okay. One of the earliest ones there, Richard Downey on the left, his little homemade type aircraft there. So one extreme to another. So just a bit of background information on what a definition of a propeller is. Where's it attached? Well, it's attached to what's called the central hub. You have radiating blades, obviously spinning around, and that forms part of what's called a helical spiral. Okay, a helical spiral. In other words, a corkscrew as it's going through the air in our case. But again, rotational water, that's two different mediums, which will produce thrust from the blades and gives the forward motion of the vehicle. But again, we still do the same thing. So again, propeller-defined hub, multiple device, which basically what we do is we change rotational power, okay, of an aircraft into what we call thrust power. And the purpose of propelling the aircraft on. Okay. Now, as we know, in an aircraft, air is less dense than water. All right, so air is quite classed as a relatively thin medium. Again, obviously compared to that of a propeller for a boat. And therefore characterised by a relatively large diameter and a fairly high rotational speed compared to a propeller on a boat. Usually mounted directly on the engine drive shaft and in front or behind the engine housing. We'll look at that later on, some examples. Now, as the science aerodynamics progressed, propeller designs improved from basic flat boards, where pretty much that's how they were, just bits of board bolted together, which only pushed air backwards. And we had now advanced to aerofoil type shapes, more like a wing. So in the early days were very, very crude. They were just an angled piece of wood bolted together and pushed the air back, but not very efficient at all, and very, very unsafe as well, some of them. Okay, so these airfoils produce lift, just like a wing on your aircraft. When the aircraft's flying through the air, the wing is producing lift for the motion of the air flying over the wing. And likewise with the propeller is cutting through the air. Just pretend to be a wing. This time it's rotating instead of moving forward. Although we'll cover that as the aircraft moves forward in a later chapter. Okay, but again, very much an aerodynamic design. So as aircraft designs improved, initially all wood, nice and easy, abundant source of material. Again, but wood, not very strong and easily broken. Can be quite heavy as well. Again, eventually we developed these thinner airfoil sections and then to provide greater strength. And then, like nowadays, we have far better technology and materials. Now, because of strength, improvements are brought through aluminium alloy propeller into wide daily usage now. Although we still have many, many wooden propellers moving about on some of the small aircraft, but certainly for more commercial size aircraft, we will have certainly more robust and easily made aluminium versions. Now, the advantage of being able to change propeller blade angle in flight led to acceptance of what's called the two-position propeller, and later what's called constant speed propeller systems. Again, we'll look at this more in depth as we go through the course. So today's propeller designs, I'm sure you've seen so many. Certainly you've got some aircraft turboprops and things like that at your airport. And some of the designs there will be very similar to what you've got in the picture there. Nowadays, so composite designs, not just wood, not just aluminium, carbon fiber, carbon and that sort of thing. We have multi types of materials, lighter, stronger, more durable. Okay, so lighter also makes it easier for starting and less strain on the engine as well. So it's materials that will help us be more efficient with propeller aircraft. So we're going to look at propeller aerodynamics. As I said before, a propeller is pretty much just a wing that's spinning on a rotational hub. So each part of propeller blade was a cross-section element similar to of an airfoil or a wing. Your aircraft will modulate your basic aerodynamics. In order to fly, an aircraft must generate a force at least equal to its weight to maintain level flight, and force greater than the weight in order to maneuver. And maneuver may mean by turning. So we need to generate a force. Now the force is called lift, and that's perpendicular to the relative airflow, or we can short abbreviate it to RAF. So back to modulate, as the wing is moving through the air, okay, the air flowing over that, we will produce a lift. Again, we'll recap this as we go through. Now, the theory is also true for aircraft propeller, but in the case, instead of being called lift, we call this lift thrust. Okay, so the principle is the same, we just change the terminology. For an aircraft wing, we need the lift, but the wing that is now rotating on the hub of the engine is now providing us with the thrust. Okay, I'll just admit this other student. Hello, Krishna. Okay. Right, okay, so that's the initial things we want to make a note of at the moment. So modulate, aerodynamics, a wing, which is a lift, the force going over the wing is going to the lift, but the lift in our case for a propeller is known as thrust. Okay, worth highlighting the difference there initially. So whenever a propeller moves through the air moving around the propeller, or the blades, or the aerofoils, as I said before, they're basically wings attached together around the central hub, will undergo a change in direction. And again, that causes a change in velocity. So a change in direction will also change the velocity. The mean by change in direction is the angle of attack. So as this will either speed up or slow down the airflow passing over the blade, it will also affect the static pressure, as explained by the equation of continuity in good old Bernoulli's theorem. Again, going back to your modulate and even indeed physics and even gas turbines as well, the Bernoulli theme, but we'll recap that anyway. So using Bernoulli's theorem, definite relationship between velocity and the static pressure can be used to explain how thrust, going back in modulate, lift, is generated. That's because it's proven that for an airflow passing around an airfoil section, the flow will resemble the flow passing through a Venturi tube, okay, due to the propeller's what we call the geometrical shape. So again, I'm just taken back from modulate, and hopefully you've all done modulate. So if we start on the left-hand side here, I'll just change my pen here. Okay, so we've got a basic tube, okay, Venturi tube here. Again, we go back to the basics of convergent, divergent nozzles. So on this side here, okay, we've got at this point here convergent. Now remember what happens to velocity, pressure, and temperature. Well, the gas that's coming in from this side, as it comes into the narrower section here, which is making this sort of triangle shape here, the convergence, well, to increase its speed, well, it's got to increase speed to get through this restricted part here, it's got to speed up. So the velocity has to speed up, and at the same point, pressure and temperature do the complete opposite, and they go down. Okay. The airflow here, the same mass, must be the same mass coming out. So velocity speeds up, pressure and temperature decrease, gets to the restriction there, and then as it comes to the outside of the tube, in this case, we now form a divergent shape. So if it's divergent shape, velocity will slow down or decrease. However, pressure and temperature will increase. Okay. Now, we apply this to an airfoil. We've got a mass flow of air coming from the leading edge of a wingtip, or the airfoils here. So as it goes over the top, to get to the same point in the back here, it's got to speed up. All right. Now, if it's speeding up over the top, it means it must be slowing down underneath the airfoil. So velocity is speeding up here, pressure and temperature on the top airfoil must be a lot less, especially more reference to pressure. Therefore, underneath that same mass flow of air to get to this side, the velocity has decreased, therefore pressure has increased. And if pressure has increased underneath, then that wing must go up the wing. Okay. The reason the velocity is decreased here, there's less distance to go here compared to the top. The top part has to go quicker to get from here down to here, whereas underneath it doesn't take as long. Yes, the airfoil is the same size, but due to the angle, the distance on the bottom is less than the distance on the top. So in other words, we have low pressure on top here, high pressure underneath, and that gives us a basic lift. So that's a recap of modulate. Now, if you apply this to a propeller, which is spinning round and round, well, as it's cutting through the air, it's making an airflow over the actual propeller. It's generating the same low pressure in the front and high pressure behind it. In other words, it's getting lift. And as we said before, lift for a propeller is described as thrust. Okay, so just a closer look at what's going on. Again, recap. So high velocity, low pressure, high pressure, low velocity. Again, that wing will move up the way. Okay, the airfoil section. Likewise, for propeller, we also get the same effects of good old stagnation points, where the airflow actually comes to a rest initially. Some of it will actually go over the top of the airfoil, and some of it will go below. We call it stagnation point. Upwash and downwash, okay? But again, that's just more recap for your modulate. But again, the principle is the same for an airfoil or a propeller blade. Okay, so there's the upwash we've mentioned, the stagnation point, and you also get what's called downwash. The point at the front of the blade on the wingtip where it will stop, go over the top, and then eventually come down, and we'll get what's called downwash. Okay. Again, hopefully this will recap from modulate. Angle of attack, again, applies exactly the same to a propeller blade as it does to an airfoil on a wing. So angle of attack, or AOA, is the attitude that an airfoil surface presents to an oncoming airfoil, and is known as its angle of attack, represented by the symbol there. And that's angle measured between the chord line and the relative airflow. So the chord line, the line that runs right through the middle from the leading edge of the airfoil to the trailing edge. Okay, and there we have it represented here. So if you pick the midpoint of the leading edge of the airfoil and cut a line right through the airfoil to the trailing edge or the back of the wing, that's your chord line. Okay. Now the difference between that chord line and the position the air is attacking the airfoil, that is known as your angle of attack, represented by the symbol there. Okay, good old angle of attack. Now, when it comes to propellers, like an aircraft, you change the attitude of the aircraft to go up or down, they change the angle of attack. On modern aircraft, we can, in fact, change the angle of attack by twisting the blades on the actual hub itself. So we do get an angle of attack. Some propellers, the small aircraft, might be fixed. They have a specific angle of attack because they're designed to fly in specific conditions. They might be fast and powerful or slower, but more cruisability. Again, we'll discuss that later on. Okay, so hopefully everybody's happy or recalls the angle of attack. Okay. Change the angle of attack will cause velocity and the static pressure, obviously, on the flow of the vary as it passes over the airfoil. The increased angle of attack, upper surface will have a lower pressure as it increases the angle of attack, and obviously on the lower side, the pressure will increase. Okay, the greater the angle of attack, the greater the lift, or in our case for a propeller, the greater the thrust. Okay. So it says there, changing pattern of the airflow around the surface affects the pressure differential between the upper and lower surfaces, which will increasing or decreasing accordingly, all depending on the angle of attack. So I said there, increasing angle of attack propeller blade will now cause the stagnation point, the bit at the start of the leading edge of the blade, to move further along the lower surface. Now, as we saw in Module 8 before in aerodynamics, as that stagnation point goes further and further down the wing, eventually we get to a point where it will tip it and will induce a stall. Okay, so we don't want that. So more upwash, increasing the distance, etc. But again, the downside is eventually we'll get to a point where we potentially get stalled. And just a recap there in the diagrams of what we mentioned already. So stagnation point at the front. Okay, and as we increase angle of attack, yes, we get more lift, but as you can imagine, we can keep going up and up and up until a point of about 50 degrees, it will get stalled. And the same applies for a propeller. If we have too much angle of attack, we can cause too much strain in the engine and also induce a stall, and unfortunately, they'll lose airflow. Okay, up past that point, there'll be no more lift. You've just got a lot of turbulent air, which is no good for a propeller or a wing, and we just get a stall. So for an airflow passing an airfoil shape, therefore the angle of attack in conjunction with the actual shape of airfoil are the principal factors in determining how air moves around it and how lift is generated. So all we're doing here is applying the principle of modulated dynamics to a propeller blade attached to an engine that's spinning, rotating around. Instead of the airfoil flying through the air, we've got a rotating airfoil, which is doing the same thing, but at basically right angles to a wing and almost. Again, any changes made, those two factors will affect how the airflow moves around an airfoil and also the amount of thrust it generates. And just for a bit quick one there, section. Oh, sorry, just to admit somebody else. Okay, right, again, blade empathy, we're going to cover that. We'll cover some topics in this one. Blade empathy will be in 17.22 later on in the books, okay, just for your own background there. Okay, this one, you hopefully remember this one from your modulate, just to recap some of the terminology. So just like an airfoil, a propeller is an airfoil, so it's pretty much got the same parts as an airfoil would have on your wing. So each part of the propeller blade has a cross-section element, very, very similar. So again, we'll start here. We're at the front or the leading edge of the airfoil, and obviously at the back will be your trailing edge, so trailing edge and leading edge. So the thickest part at the front, okay, there's your chord line running right through the center, so that's your chord line there. A chord line is very similar to it. It's called your mean camber line, which pretty much follows the average distance from front to back and depend how thick that airfoil is actually as well. Your maximum thickness point, okay, max camber, the upper surface, lower surface, chord line mentioned, mean camber line, and that's pretty much it as you saw in modulate. Exactly the same principle that we're going to look at in propellers as well, okay? So there should be no difference there. Just a quick one, has anybody not done modulate? Has anybody not seen this before? Just to make sure I'm not starting fresh with anybody, because hopefully you should all have done modulate before you've done module 17. Okay, if science is good, if you've all done it, good stuff, and hope you all passed that, hopefully. Right, moving on. We're going to look at the actual propeller now, propeller blade assembly, the basic components that actually make up the propeller. So we've got the blade tip, as it sounds, this part here. We've got outer edges of the actual propeller. The blade shank, okay, it was just about here. Okay, it will vary in design slightly, but it's just before the main fitting of where the propeller fits into the hub. So we'll call it a blade shank. Surface, okay, will be certain marks in this one, and the same wise, the lower surface will be the pressure face, which in your case for a wing would be the under part of the wing, the bit that actually provides the lift for an airfoil, in our case the thrust. So that would be behind this one here. That's where all the power comes from. Pitch change pin, this part here. Now the pitch change pin, this is on a bearing, so it allows the propeller to twist in the actual hub, all controlled by a certain mechanism. Again, we'll cover that further in depth in the book. So I say that just allows the propeller to rotate. Bearing races and faces, yeah, you have the bearing races and faces all within the same sort of area. There'll be a bearing attached to the pin. That will sit in a housing, attached to some sort of linkage, which will help rotate the propeller. Leading edge protection strips. It says they're nickel, they're usually made of nickel. Yes, they will have depending how far along they go from there. Okay, and all they are obviously these leading edges are in the front line of the airflow. Obviously rotating very high speeds. Anything that's in there potentially could hit them or damage them. It gives an extra bit of strengthening and helps support the blade as well. And any impact damage, hopefully it absorbs some of it. It won't absorb all of it, unfortunately, but it will certainly give a good bit of protection should anything try and fly through the blades, especially if in our case, birds, any other type of FOD as well. Anti-icing boots, this sort of dark area here, just along your leading edge. These will be electrically controlled anti-icing boots, or de-icing boots as we call them. So anti-icing, sometimes called anti-icing, usually called de-icing. Now de-icing Anti-icing system is usually hot air, where de-icing is electrical, which allows ice to build up and then small accumulations and melts it off in one go. But again, we'll describe this a bit more in depth as we go through the course. Okay, and then the blade cuffs. Again, these will be fit around about this area here. All right. Again, we'll speak at these more in depth and more better diagrams hopefully as well. And then what was called master station identification. Usually a yellow band, roughly about half to 2/3 of the way along the blade. Okay, and again, just be aware of all these parts for the moment because we will go more in depth through the course. Okay, so that's the basic breakdown of components on a propeller. Again, they do vary from propeller to propeller, but this is the main ones we'll look at as again each part of the course. So the propeller is one thing. It fits in what we call hub assembly. Also, the bit it joins into that's attached to the shaft of the engine or the gearbox, and where it's allowed to rotate, or if it's fixed or whatever, whichever version it has. Okay, so we need some sort of hub assembly. And there's some couple of examples we've got there. The center part where the propeller fits in. Okay, I can see here, there's one propeller that side, another propeller that side, or indeed you can have 1, 2, 3, 4, 5, 4 in this one, 2 in that one, 3 in that. It all depends on the type of aircraft and how many propeller blades it requires. So the hub casing, some sort of insulation flange where it bolts onto or clamps into. Some might have what's called centrifugal counterweights, and that helps with vibration. Again, just be aware of these for the moment, but we'll describe them later on. Some sort of cylinder, it could be static, it could be movable. And what I mean by a cylinder, it's a cylinder that will have either a spring and oil pressure, or it might have oil pressure both sides. And depending on the system, that will allow the propeller blade to twist inside the hub to change the pitch of the blade. In other words, to change the angle of attack. And there's a couple of systems that we'll look at further in the course. The cylinder as well will have a piston. Again, the piston will be in there as it sounds, just like a piston on an engine. It moves back and forward. And again, depending on the type of piston, we'll have either oil on one side or it might have oil on both sides. And it could be internal or external as well. Again, just be aware of the types for the moment. Piston change links, again, external, internal, and these are the ones that connected, again, to internally or externally to help move the pitch of the propeller. All in conjunction with the previous parts we just mentioned there. And then we've also got a feathering spring. Now, a feathering spring is attached to what's called a single acting piston. Again, a quick insight, we'll just jump ahead a little bit. This spring, quite a large spring, it's about 1 foot long on some of them, under a lot of pressure. So when the engine is running, you will have oil pressure one side, which is acting against the spring, which, depending on how much pressure is there, will depend how much that blade is moving or which angle of attack. So imagine when the engine shuts down, you lost the oil pressure is not there, so the spring will take over, and that will put that into what's called the feathering position. Okay, so just be aware of that for the moment. Again, we do go this more in depth. And we've also got what's called flight fine and ground fine stops, internal or external. And this is the minimum position of the blade, or the fine position, where it's cutting through there nice and easy, to what's called a ground fine, where it actually stops, it gets located in there. Okay. And it can go past that, it can go past into reverse thrust on certain aircraft. Again, we'll look at that as we go through the course. Propeller assembly. On the hub itself, you'll have some sort of spinner assembly. As it sounds, it's spinner. Within that spinner, there's quite a few components. We need electrical power to the de-icing boots, anti-icing boots. We'll have a spinner cap for a bit of aerodynamics. We'll have bearings in there, we'll have seals, we'll have pistons, quite a lot going on as well. So there's not just a hub bolted on propeller on there and that's it. There is quite a lot in there as well. We have a back plate, this one here. Some sort of anti-icing, de-icing slip ring. The slip ring is like a car steering wheel. In your steering wheel in a car, you have a slip ring, and that allows you to use controls, the electrical controls. So your indicators, your window washers, wipers, and that sort of thing. You need power. Now, you can't just put cables on there, because as you would twist the steering wheel, the wires would get all mangled up. So basically, you've got what's called a slip ring. And a slip ring is just a big disc, and you have contacts which are on springs that push against the disc, but as the disc rotates, the spring and these carbon bushes will touch there, and that provides your positive and negative to the power source of various connections. Okay, and for a propeller, it needs the same thing. We can't have wires attached there because it's going to spin round and rip off, so we use what's called a slip. And again, the anti-icing or de-icing electrical bushes or brushes, same sort of thing. Root cuffs, just to help aerodynamics. Okay. And there's a better diagram of some of the parts we've got there. So at the front, we've got a spinner, got some sort of cones, again, we mentioned these later on. Some sort of de-icing system, electrically heated. Spinner bulkhead. Oh, somebody's got the microphone on. Your slip ring assembly. There's the brushes for your electrical contacts. Very crucial. So again, if you come to maintain these, you should be checking the length of them, make sure springs working, they're clean. Essentially, a lot of problems that happen with these is dirt. Imagine in the air, the engine, oil, space, stuff like that as well. Dirt can cause a lot of problems with brushes. These brushes, washing machines, start motors and cars. Very, very similar idea. Okay. Again, so that's all fit together. We're just looking inside, and I'll just point out here, you can just see on number 8, these are what's called your centrifugal weights. Okay, again, we'll mention these, but just be aware of them for the moment. And then it'll be fitted to your hub assembly by a couple of different methods. Again, we'll cover this as we go through. Right then, relative airflow or RAF, again, what used to be in, but it's not that anymore. Airflow and speed, again, for module 8, is the same principle again. What is the relative airflow? It's the resultant of two components. Okay. In this case, the propeller is the rotational speed, or your RPM, your revs per minute. The aircraft speed, IS, indicated aircraft speed. I'll produce the speed and direction at which the airflow meets the propeller blade. So remember, as the propeller blade is spinning round, the airflow will, like a wing, with the wings going like that, the airflow is touching the wing. This case, propeller spinning round, it's inducing the airflow going over it. So depending on the pitch of the blade will depend on the angle of attack from the chord line to relative airflow. And the greater the attack, the greater the thrust. Okay, all dependent on the engine speed as well. And direction of airflow against the blade will be at an angle. Okay. Any questions so far as we move on? Anybody happy so far? Yeah. Okay, plane rotation. The plane rotation, as it sounds, it is the rotation of the engine, obviously spinning, and it's the right angles to the center line of the propeller axis. All right, so you've basically got the engine shaft coming through, but your propeller is spinning pretty much at 90 degrees to that. That's your plane rotation. Now, some aircraft will rotate clockwise, some propellers will rotate anti-clockwise. Most of them are anti-clockwise, but again, it all depends on where the aircraft was made. Right. Thing important here is to highlight in your books is the speed of rotation is directly proportional to the engine speed. Okay, so speed of rotation directly proportional to engine speed. So it's certainly worth highlighting that. Angle of attack mentioned already. Again, angle of attack is a chord to relative airflow, like you saw in the previous diagram. So just a slight recap there. Now your blade angle is normally acute, in other words, less than 90 degrees, between the chord of an element of a propeller blade and the plane of rotation. I've got a diagram come up, so make all sense of this. So when the pressure face is curved, like most airfoils are, the blade angle is always measured with reference to the blade chord line. So we'll show you what it means in the diagram in a minute. The angle of attack varies with changes in propeller speed, RPM, and also aircraft speed. It takes a bit of time getting used to this. As you imagine, the relative airflow angle of attack is going to change. The faster the aircraft goes, we'll look at it, the angle of attack is actually going to decrease. But again, we'll show you in the diagram shortly. Blade angle will result in lift and also drag. We don't get nothing for nothing, unfortunately, on the blade element, as it does with a standard airfoil, like we saw in Module 8. In the propeller, the emphasis is not as much concerned with the forces perpendicular and right angles or parallel with airflow. In other words, lift and drag, but centers on the force acting along the axis of the actual aircraft. So your horizontal axis, we're looking at the forces acting against the axis. In other words, we've got the thrust force, and at right angles is the rotational, the torque force. In other words, the total reaction on the blade is therefore dissolved into thrust, which we use lift in Module 8, and also torque. Well, torque is still torque due to the rotational forces acted by the engine. Have a look. So again, there's a standard airfoil. Okay, and we've got our vectors. Let's put some information on there. So thrust is going forward. Now remember, that'll be felt on the underside here. Thrust in Module 8 was lift. So the propeller blade, as it's spinning round, is producing lift, but as we know it, we now call it thrust. So hence a change in the vector terminology. The torque force is due to the spinning of the propeller along the axis of the engine. And between the two, you get your resultant force, which is your total reaction, the point where it is actually going through. And you have your pressure point right below there as well. Okay, all depending on the angle of attack, all depending on how fast that engine is rotating. You also have the forward direction of the aircraft. The faster that gets, these vectors will change as well. There's a direction of rotation, okay, it's coming towards me there, and your direction of airflow, your relative airflow. Okay, so you can imagine if we change the angle of attack of the airfoil by mechanically changing it, that will also change the angle between there, which will give us increased thrust or less thrust. And likewise, it will do the opposite with speed. It will increase torque or decrease torque. Now, the difference between these lift and drag can be seen in the following diagrams. Thrust is a propulsive force, or the lift as we knew before, and torque is the resistance to rotation. Torque, like any sort of thing we speak about in any of the modules, is a twisting motion, now from opposite. That'll be a relative airflow there as well. Now that's your normal angle of attack, okay, as you would find on your wing. Then we've got the blade angle. Now the blade angle is the whole angle between the chord line and the plane of rotation. So there's three things you're going to look at. Angle of attack, yes, your normal relative airflow to angle of attack of the chord line, that small part there. The blade angle is the whole part from the chord line to the plane of rotation, the way it's spinning, 90 degrees. And then we've got the helix or angle of advance, which is this part here, okay? So it's only this part here. That's your helix angle, or also known as your angle of advance. Okay, same there. twist, as it sounds, the rotational speed of any part of the blade depends on the distance from the propeller axis to rotation. Now, we need to have blade twist or washout. In the early days of propeller manufacturers, they were just planks of wood set at one angle on both sides of the hub. No twisting of the blade, no washout. So yes, they could move air backwards, but not very efficiently. Very, very crude. So by giving the blade a twist, same as a wing in an aircraft, we can get far more energy and maintain that flow across the wing, in our case, the propeller. So its rotational speed of the blade tip is greater than that at the root. So imagine, obviously, as a blade or a wing is flying through the air, the airflow is pretty constant. Airflow because the wing is quite constant, but as it goes over the wing, it does vary slightly, but we try and maintain that flow as best as possible. On a propeller, as it's spinning in the center, it's going quite slow, but as you get further out to the propeller tip, that tip is going a lot faster to maintain the same momentum. Okay, so the closer to the hub, the slower it is. Out towards the tip, the faster it's going. So hence we need this twisting of the blade to maintain the actual velocity of the airflow over the propeller. However, though, forward speed of the propeller is the same at all parts on the blade. Okay, forward speed, so it's all good. Relative airflow is dependent on two velocities. Rotational speed, that makes sense, obviously how fast the engine's spinning. And also forward speed, the airflow of due to the aircraft flying through the air will also affect it as well. Therefore, it can vary along the length of the blade and producing varying angles or various angles of attack on the blade of a constant angle. So the pitch of the blade, or the angle blade, can be set, but depending on what's happening with the speed of the engine, the speed of the aircraft that flies through the air can also affect the components there. So the blades on propeller are obviously designed by the manufacturers to get the most out of it where possible, provide that maximum amount of thrust where required. So in order to maintain a constant angle of attack along the blade angle is reduced from the root to the tip. Okay. And this gradual decrease in blade angle from the hub to the tip is called blade twist or washout. Exactly the same as modulate. We had washout, twisting the blade, the wing to the root tip. Okay, but we call it blade twist. The thrust of the propeller is obtained by the fact the chord of each part of the blade is inclined at a smaller angle of attack to the direction of rotation. So as it comes further out towards the wing, the propeller tip, it gets slightly less. The blade angle is reduced from root to tip. Okay. Again, good one to highlight in your books. Make sure you remember that. So there we go. Just put another diagram up there. On the front one here, forward direction of the aircraft. So colour code there, your tip, midsection, and then right at the root, you can see the twisting going on, and certainly more proficient here. So if you look at the root here, and then you can see the twist. It's like you've got grabbed the blade, just twisted it. Okay. In this case, this propeller here would be spinning anti-clockwise. That would be actually rotating away from the diagram at the moment. Okay, so that's your washout, exactly the same as an airfoil. Now, important thing to remember here is in this diagram especially, and you can see this here, that tip there, washout always goes downwards. It never goes up the way. It's always pointing down the way in the rotation of the propeller. Because imagine if it's pointing up the way, as it's rotating, it would give a lot of force going the wrong way. So it's like as a wing on an aircraft, the washout is always twisting towards or down in the forward direction. That's an important thing to remember there as well. Okay. So, just we'll go for a quick break. Components and forces acting on propeller, just sort of bring them back in line. Looked at that part already. We've got the thrust, which was the lift. You've got your torque from the rotational speed of the engine, which gives you a resultant. So that's that bit we looked at earlier on. The chord line, as before, going through the centre of the airfoil section. Angle of attack was against the relative airflow. Oh, guys, keep your microphone's off. The blade angle was the whole angle between your plane of rotation and your chord line, and then your helix advance was as we showed already. Okay, just a bit of recap there. So a lot of forces acting on it. And then the helical path, as this is all twisting going forward, we get what's called the helical path. So when the propeller is operating in the flight range, in other words, it's in a positive angle of attack, the propeller is both rotating and advancing forward. In other words, it's trying to pull the aircraft out. As it's flying, corkscrewing through the air, it's grabbing, it's like you're in a swimming pool. As you're swimming through a swimming pool, you're pushing the water behind you. Likewise, propellers trying to push that air behind it. Okay, so it's trying to go forward at the same time as it's spinning rotationally. So a corkscrewing type effect or a helical version. So you can see this green one here. As it's going round, it's trying to corkscrew through the air. So direction motion of propeller, we call that the helix. Instead of a straight line, every section of propeller blade travels at a different helix or a helical path. The helical path element consists of a combination of two components. One component is the resultant of your rotational RPM, so it depends on the speed of the engine, and also, again, of the speed of the aircraft. In other words, it's going to increase or decrease depending on both the speed of the aircraft and speed of the engine. You have quite a large helical path or quite an intense short one. In other words, if you like a high frequency or a low frequency. And this is it shown here in your books. So there's your propeller. A is represented here by the tip of the blade, so you can see the path as it spins through the air, it's trying to go forward, an advanced revolution. The closer you get to the center, obviously there's not as much movement, and obviously at the center of the hub, it should be a straight line. If it's not a straight line, there's something seriously wrong. All right. So in theory, that's how far at tip should go in one revolution. But there's a few factors we're going to look at that prevent that. Okay. So leave that for the moment. What we'll do is we'll go for a little break. Well, before we break, has anybody got any questions you'd like to ask at all of what we've just covered so far? That basic background, you see most of the time, or so far, it should be Module 8 recap. And all we're doing, we're getting a wing and then putting it 90 degrees and putting it on an engine and spinning round. Okay, but the principle is very similar to what we've seen in Module 8. Any questions from anybody at all at the moment? Hope you're not all fallen asleep so far. All right. All good? Right, what we'll do, folks, we'll go for about 15-20 minute break at the moment. Cups of tea and whatever. And then we'll rejoin you shortly. Okay. So I'll just put that up for the moment. All right. Okay, folks, we'll see you in about 15-20 minutes. I'll come back then. Thank you very much. He's stuck. It's frozen. He's clever, you see. He's got a photograph himself, pretending he's online. Try on. Go on, JMass.
Yep.
What is the name you use for lift for propellers? The same force, but in aerodynamics we call it lift, but in propellers we call it what?
I have no idea, man.
So the force, obviously, the wings flying through, the force we get is a lift. But a propeller spinning round, it's the same principle, but we call it a different name. Instead of lift, we call it something else. Yeah.
Helical path.
No idea. Thrust.
Sorry? Sorry, James, say again.
Thrust force?
Thrust, yeah, thrust. Instead of lift, Module 8 aerodynamics is called lift. It is the same sort of idea, except we call it thrust, that's all. We just call it thrust. It's the same principle. Instead of a wing flying through the air, we've got it going round and round. There he is. That's Manny's back. He's unfrozen. Good man. Okay. It's happy. Who else is wanting in? Right. What is washout? What is washout? And we'll go for Saroj. Saroj, you there? No. Go. See, Parasmani going frozen. Go for him. Parasmani. Can you hear me?
Yes, sir.
Yeah. Can you tell me what washout is, please? What is washout?
That is blade twisting, sir. Decrease of blade angle from up to tip, root to tip.
Yeah, from root to tip. Good. Thank you very much. Good.
Okay.
Good. All easy stuff so far. For a bonus point, I don't have your name on the bottom right there. Your names that come up on the screen. You're number 16. Whatever that's come up as. I don't have your name there, but you're number 16. Number 16.
I'm M. Kumar Dal, M.
All right, I don't know why your name's not come up for some reason. You just come on as number 16. With reference to washout, the tip of the blade, does it face down the way or does it face up the way at the tip?
I didn't get it.
When you look at the blade twist or washout, like Parasmani mentioned, the tip of the blade, does it twist down the way at the front, if that makes it easier, or does it twist up the way at the front, at the tip? So we twist the blade, so at the tip of the blade, does the end face down the way, or does the end face up the way as it's twisted?
It is.
What do you think?
Twisting blade up and down.
Yeah, so you just, Parasmani mentioned the twisting, the washout, the twisting of the blade from the root to the tip, yeah? So get the twisting to maintain the airflow velocity along the blade. But at the tip, does the twist go down the way, or does the twist go up the way?
In the tip,
Yeah, at the tip of the blade. The very end of the blade. Does the end of the blade twist down the way, or does the end of the blade twist up the way?
down, I think down.
Good guess. Yeah, good man. Twist down the way. There's no point in twisting up the way, because if it twists up the way, as it's rotated in the direction of rotation, it'll try and push the blade back. So it's naturally tending to twist down the way, exactly the same as a wingtip on a normal aircraft. Yeah, so we twist the wing from the fuselage to the tip, and it's also facing down the way. So the tip of the propeller blade is also twisting towards the front, or down the way, if that makes sense. Okay, good. Okie doke. Right, that's a couple of questions there. We shall move on. Any questions from yourselves, guys? Anything you want to mention or you want to go through before we move on? All happy? Yeah, I've got some shy people there. Some people with videos. I can keep your videos on, please. Let me see you're still alive, you're not got COVID, you're awake, and that sort of thing. Okay. Oh, he's eating. Good man. You're making me hungry now. That'll soon be lunchtime. Good.
I'm going to turn off my video.
Time. It's almost 6 hours time difference, isn't it? So it's only 10 to 11 in the morning here, and it's almost night time for you guys. All right. Okay. Everybody happy to move on? Yeah.
Yeah.
All right. Let's move on next bit. So we finished off there just before tea break. Helical path and what happens to the tip of the blade, the middle of the blade, and the centre of the blade. We get a helical path. In other words, it's trying to corkscrew through the air as it's going forward. Yeah, it's trying, like you're swimming in a swimming pool, you're pushing the water behind you, the tip of the blade is trying to rotate forward. And that was a helical path. So look at some variations of forces along the blade. Propeller blade is shaped to make the most use of each blade element, and we'll look at the certain elements as we go through. Only proportional blade is effective due to losses at the root and at the tip. Now, what I mean by losses is aerodynamic losses. There could be slight bit of turbulence, the speed at the root to the speed at the tip. The tip obviously gets thinner. As it gets from the root to the tip, it does get thinner, so it's not quite as effective as it was maybe halfway to 2/3 of the way through. The propeller blade tends to get most of its thrust or most of its power from about 2/3 of the way in the blade. At the centre, it's not going as fast as the tip, But the string there, the tip's going fast in the centre. It's the middle area that does all the work and support. So we do get a little bit of loss there, unfortunately. So there we go. Blade is most effective 2/3 to approximately 3/4 of the distance from the blade root. So it's a good one again, highlighting your book. So the most effective point is about 2/3 to 3/4 of the distance. That's where it's the strongest point, or certainly one of the best points and thickest points. You get the most effective thrust from there, or lift. If we kept the propeller blade the same thickness all the way through, then be a lot of momentum at the tip blade, a lot of force, a lot of strain the blade, so we have to taper it off, okay, just to make it a bit more viable. And there's a graphical representation. So you've got thrust and torque on the left-hand side there, and then you've got your blade section elements, okay. And they're actually portioned off. We'll go into it later on. They need to actually a certain distance, okay, and we'll come into this in a bit. But they're about there, so 2/3, 3/4 of the way. That's where you get the most thrust, you get the most torque. Now, as the blade gets thinner and smaller, then we start to lose efficiency of the blade, okay. So the strongest point, or the most effective point, most efficient, is roughly 2/3, 3/4 of the way. There with tip losses, yeah, you definitely got induced drag cause of tip losses. So hence when we do the washout, we tip the blade towards the front, we make it nice and round or smooth or airflow as possible. Inevitably though, you're going to get vortices, vibration and turbulence. Again, I use the swimming as an analogy. When you're swimming in a swimming pool or in the sea, when you put your hand forward in the water, you get lots and lots of bubbles pushing the water back. And the exact same thing with air. Anything flying through in air, the extremities of the airfoil, the fuselage, undercarriage, whatever it is, in this case propeller, you're going to get vortices and turbulence, unfortunately. So we try and minimise that where possible by shaping the propeller into correct profile. You'll never get rid of 100%, you can certainly minimise it as best as possible. With lift, 4 forces acting on an aircraft: lift, thrust, weight and drag. Well, if we get lift and thrust in our case, unfortunately, we're also going to get drag, purely by just having something in the air. Something spin the air is going to cause drag. Yes, we can make it as efficient as possible, but we will always get a little bit of drag. We never get rid of drag, unfortunately. Okay. So at high-tech speed, further losses could cause by compressibility effects. Propeller blades are designed to be a certain distance. We can't make them massive long ones. We can, but we've got things like ground clearance. Okay, Andy, thanks. Catch you later, bud. Good to see you back, Andy. Wind turbines, they're massive blades, but they don't spin very fast. Okay? Can you imagine the tip speed of the blade? It's going to be absolutely massive compared to the centre. So you got to think, the bigger the blade, the faster the tip's going to go. So we get to a point of potentially the blade could actually go supersonic. Now, propeller blades don't go supersonic. If they go supersonic, there's only one thing going to happen. The blades are going to go flying off, disintegrate and break out. So we've got, well, not me, you guys potentially, you become designers as engineers, have to design an engine that's suitable for the power for the aircraft, the size of the aircraft, and the propeller or propeller blades that's suitable for the speed of the engine and the power required to propel that aircraft forward. Okay, so you can't have massive propeller blades. One, because it spins round, it's going to hit the ground, not very good. And likewise, if it's too small, we're not getting enough power as well. So it's up to the designers to make sure the right length, the right size and shape. Again, we'll cover this a bit later on. Root losses. We spoke about tip losses, turbulence and that sort of thing. Again, you will get some at the root, the base where it joins the hub. Now the thickened root withstands high stresses, but it does lose aerodynamic efficiency. So there's a few things we can do to help that. The airflow at the root may also be affected by where the engine is and the engine intake. Okay, so the type of engine you might have might affect the airflow around the engine and the propeller. Some large turboprop blades are fitted with what's called blade cuffs. Again, another thing to highlight in your books. Blade cuffs, they're like an airfoil covering to help prevent vibration and turbulence. And you can see here, They're just covers. That's all they are. They're just airfoil covers that fit over the shank of the actual propeller and just help promote the airflow around the centre part, the slower moving part of the propeller. Okay. We don't want turbulence, and we certainly don't want turbulence. Now, some of the intakes on engines that are behind the propeller, the intake could be very close. And if you're getting turbulent air going from propeller to the engine, that can cause problems for the engine. So if you can get smoother flowing air going towards the engine, it certainly all helps. In principle, propeller, when a propeller takes in air, like I said before, we get a low pressure created in front of the blade, which should be the top of the wing, due to the camber of the blade back and upper face. The low pressure area behind the blade in the lower face produces thrust, which causes tension in the propeller blade and pulls the aircraft through the air. Okay, so the amount of thrust will depend on several factors. Angle of attack. Yeah, like an aircraft, we change the angle of attack, will increase the amount of lift. Like a propeller blade, we change the pitch on the blade or change the angle of attack, that will also increase the amount of lift, as we know it is now called thrust. How fast those blades are moving through the air, yeah, like an aircraft wing flying through the air will get more lift if you make it go faster. Same as propeller blades, we spin them faster, that will give us more thrust, which will give us more power. Okay. And also the shape of the propeller, the shape of the airfoil. You get sporty versions, you get commercial versions, you get basic versions, you get lots of different types of versions. The blades themselves are designed specific to that type of aircraft, whether movable, fixed, or whatever. So what we're going to do now, this is where some people get a bit confused, but it's easy to get lost in this one, so hopefully not too bad. So I'm going to look at variations in the angle of attack. So the chord line through the airfoil, the propeller, to the relative airflow. So some basic diagrams will hopefully make sense of this. So what we're saying here is we've got an angle of attack, okay, from the airflow coming in as the propeller is spinning around, and there's no forward velocity. What mean the aircraft isn't moving? Okay, so the aircraft's on the ground, the propeller's spinning, whatever angle of attack it's been set to, that will give us however much pressure there, however much thrust. Okay, so for instance, we've got a 45-degree angle of attack. This is on the ground, aircraft is not moving, no forward velocity. Okay, if you're happy so far. We're starting to move the aircraft. What have you seen? What's happened so far? What's actually happened here? So we go back to that one. Aircraft isn't moving. Now the aircraft is moving. What's happened here? Don't worry about the angle. I meant to change the angle. We'll pretend the blade is in the same position it was designed for. All we've done, we've let the brakes off the aircraft. The aircraft's now moving forward, but the angle of attack has decreased. How do you think that? Why do you think that's happened? The speed is still the same, still rotating the same speed. We've not changed the angle of attack of the blade physically, but by moving the aircraft forward, the angle of attack has now decreased. Anybody think why that could be? A lot of pens at something. Anybody got an idea of why that might be? So we've not physically changed the mechanical angle.
Because of the direction.
We've not changed the speed of the engine. Say again?
Because of the direction of the relative
I think directions of relative airflow changes.
Yeah, basically these. Yeah, sorry, go on. Yeah. Who's speaking there? Sorry, when you go. No. Okay. Easiest way to think of this is there's your angle of attack. Yeah. As the aircraft goes forward, the angle of attack decreases because the aircraft, the easy way to remember this, is catching up with the airflow, if that makes sense. Okay, the aircraft is catching up, which will decrease the angle of attack against the relative airflow. Okay, so by keeping the engine constant, keeping the pitch constant, but the speed of the aircraft getting faster, it will actually decrease the angle of attack between your chord line and your relative airflow. Okay. Does that make sense? Anybody lost there so far? So we've not moved the angle of the blade, we've not changed the RPM, but the aircraft has, we've let the brakes off the aircraft, we were static, we've let the brakes off, aircraft is now moving forward, so it's now trying to catch up with the airflow. All right, so hence you get the angle of attack decreasing as the aircraft goes forward. Okay, until such a point that if the aircraft got fast enough, there would be no angle of attack, or very, very little. So we get to the point it wouldn't get any faster. It would actually start to slow down because the propeller would act like a drag, big airfoil drag part. Okay, so on the ground, brakes on, engine spinning, we've got an angle of attack. As it goes forward, the aircraft's catching up with airflow, the angle of attack from your chord line to your relative airflow decreases. Now, what's going to happen here is, unless you change the throttle setting, it's actually going to get faster. The engine will get faster because there's less resistance in the air. Okay, the angle has decreased, so there's less air to try and push back, so the propeller will actually try and speed up. Now, we'll look at systems later on that control this, but if we didn't have a control system, what would happen is the propeller would actually get faster and faster and faster. So to increase the angle to get back to 45, we'd have to move the angle of attack physically of the blades to get back to the 45 if we wanted that. And that's what happens at cruise. When an aircraft takes off, it's a very fine pitch of angle of attack. Lots of power, lots of rotation, not very fast taking off, but it will get there. Once it gets to altitude, once it got forward speed, they will then coast in the blade, in other words, increase the angle of attack of the blade, so it just cruises. It's like going up your gears in your motorbike or your car. You don't just drive about in first gear all the time. Maybe you do, maybe on the wheelies and that sort of thing. You will change gear. So the engine isn't going really, really fast. You'll use the gears. We don't have gears in the aircraft, but we can change the pitch of the blade to let the engine cruise once we get the forward speed of the, in our case, the aircraft. Okay. So there again, there's us with the forward velocity. The aircraft's moving. We've got a small angle of attack. So as I said, the aircraft begins to move forward. The relative airflow will change direction. In other words, it'll try and catch up with the blade. In addition to rotating, the propeller is also moving forward. All right, but the aircraft's moving forward. So combination of propeller rotating and forward motion, the aircraft produces what's called the resultant relative airflow that is not directly opposite the movement of propeller blade. So it's not as it was when it's static. Okay, due to the fact we've got forward momentum, forward motion of the aircraft, in other words, the blades attached to the aircraft moving forward, we're catching up with the airflow. We're going to decrease. So a good way to remember is increased forward speed, decreased angle of attack. Okay, that's the easiest way to remember. Increased forward speed, decreased angle of attack. Okay, by not changing mechanically, that's just purely relative airflow. So increased forward speed of the aircraft, decreased angle of attack of the propeller blade, your chord line and your relative airflow. So there we go. In this case, angle of attack will always be less than the blade angle. Remember, the blade angle was your angle of attack plus your helix angle, the whole angle. But when you've got forward speed, the angle will always be less than your blade angle. So again, forward velocity, based on how the forward speed affects the airflow, acting propeller blade, it can be determined that for a certain propeller speed, in other words, the faster, like I just said, the faster an aircraft moves through the air, the smaller the angle of attack on the propeller blade. Okay. Hopefully that makes sense there. So as potentially could happen, the angle of attack could get so low that the aircraft's going really fast. And the propeller just acts like a drag. It's not actually doing its job. It's actually going slower than what it needs to do. So fast aircraft moves, smaller angle. So whatever one does, the other one does opposite. Likewise, if you slow down, if you slow the aircraft down, then the angle of attack will increase. So it will do the opposite. Okay. So therefore, propeller speed increased, the velocity of the airflow increases onto the propeller. So if we actually put more power on the engine, we're going to spin propeller faster. Well, if we spin propeller faster, we induce more airflow. If we induce more airflow, we increase. So as propeller speed increases, the relative airflow strikes the blade at a greater angle, and the angle of attack will now increase. So what we're doing there is we're combating the decrease in forward speed by the fact that the aircraft's going faster, it's decreased angle of attack. So to maintain that angle of attack initially, we need to put the engine faster, and then that will also increase the angle of attack. Now this is all controlled normally automatically by set control systems, which we'll describe later on. It can be controlled manually by the pilot. The pilot can choose more power or less power, depending on the flight conditions. Okay. And also by changing the angle of attack on the propeller itself. So, most effective angle of attack for a propeller is between, anybody guess? You go back to Module 8. What do you think? What was the general angle of attack for a good basic flight? Quite a small number. 4 degrees, thereabouts. Yeah.
3 to 4.
Yeah, 3 to 4, 2 to 4 degrees. That number there is also the same as your, remember back in aerodynamics, your angle of incidence. You remember where the wing is attached to the fuselage? It's also then you've got a positive angle of attack, which is about, again, 2 to 4 degrees. Strangely enough, with propeller blade, it's also about 2 to 4 degrees. Okay, so most effective angle of attack. All dependent on engine speed, but a basic one is 2 to 4. Any angle of attack exceeding 15 degrees is unaffected and will cause a propeller stall. Exactly the same as a wing. If you have an angle of attack increased above 15 degrees, the pressure zone goes down towards the trailing edge and gives you aircraft a stall. Exactly the same for a propeller blade. You will also, if you go past 15 degrees, you'll get a stall. In other words, there'll just be lots of turbulent air, and that will be it. Okay. So just recapping there again. So there you go. Typical propellers with a fixed blade angle are designed to reduce an angle of attack between 2 and 4 degrees, like we saw already. So a fixed pitch propeller. What I mean by fixed pitch? The propeller can't move. We can't physically move it. We can take it off. We can put a different pitch on there if we want. So a smaller aircraft, maybe just little Cessnas or something like that, you know, they're a fixed pitch propeller. They have a predetermined angle of attack, so they can only go so fast. Even with their engine speed they've got, they will only go so fast. If we can change it from a fixed pitch to a variable one, then we can get faster moving aircraft using the same engine speed. Now, either at climb or cruise airspeed with a specific RPM setting. Okay. Speed with a fixed pitch propeller, any alteration in airspeed will change the direction of earth airflow and the angle of attack will vary. Okay, so just like recapping before with forward speed. So therefore, an increase in airspeed will also decrease the angle of attack. Okay, just a recap there. As angle of attack decreases, the load on the propeller, the torque is reduced. There's less force because the angle of attack is, if you can pretend my front hand is cutting through the air like that, yeah? There's a lot of air I'm trying to push. As the angle of attack decreases, then I can cut through the air nice and easy. So there's less force on my hand as it cuts through the air, okay? So what will happen is the engine probably speed up. But the more angle of attack, put that there, if I increase my hand to give increased angle of attack, I'm trying to push all this air, that's a lot of force against my hand. Same as a swimming pool, yeah? You more water you push behind you in a swimming pool. If you put your hand like that, you can cut through the water very quick. So a decrease in angle of attack reduces the torque. So you can imagine the other way about, if you increase the angle of attack, then that's going to increase the force, torque in this case. In other words, put a lot of strain on the propeller. So reduced propeller torque will allow the engine to speed up, which is good and bad because we might not want the engine to speed up. So we can control it manually by using a throttle lever, or we can control it using a PCU or a CSU, and we'll cover these later in the books. Until we get the engine to match the conditions of flight. So with a fixed pitch propeller, an increase in airspeed would result in an increase in RPM. And why is that? Because your angle of attack has decreased. Okay? Forward speed decreases your angle of attack. So if it decreases angle of attack, your engine speed will go up. Okay? Unless you adjust the throttle to match that. So that has a limiting effect on the aircraft's performance. In other words, the maximum speed the aircraft is limited to prevent engine overspeed. So when you're getting a faster moving aircraft, you have to watch how fast your RPM is doing and bring the RPM back so you don't overspeed your engine. You can imagine if the aircraft's in a dive, high forward speed, well, potentially really, really small angle of attack of the blade, engine can overspeed and blow your engine up. So you will be keep coming down. So you don't want that. So engine speed. Change in engine speed also vary the relative airflow and so affect the angle of attack on your fixed pitch propeller. So remember, if you increase your engine RPM, you will increase your angle of attack. Likewise, if you decrease your RPM, you will decrease your angle of attack. Forgetting about the forward speed of the aircraft at the moment. So a few things there to try and get your head round. Okay, but we'll recap these before I finish today anyway. No, don't panic too much there. Anybody confused so far? Don't be shy. Takes a little while to get around it, but hopefully most of you guys are working some of this stuff anyway. So I hope it's a bit refreshing. Or if you haven't known this before, brand new to you. Okay. But we will go over this a lot of times. The questions I'll give you, I'll give to Sanjeev to print out, hopefully. If you're not where you get them, I can send the questions individually. So I might have to get your emails individually to send you the questions for your own revision. If you're not, some of you at different houses. Are you all in Nepal? Or is anybody not in Nepal? Is it everybody in Nepal at the moment? Yeah.
Yep.
Okay, good. So can you all get to Nat, to Sanjeev, or would it be easier to send you revision questions to your emails? Because what I can do is send the questions to Sanjeev and he can email them out to you, or you can pick them up from Sanjeev.
I think you can send in a chat. You can attach the file.
All right, okay. I'll send him out and then he can distribute it to yourself. Yeah. What it is, there's lots of open questions. We will keep in the book at some point once you've changed the book. But at the moment, we'll give you the questions and we'll give you the answers as well. Okay, but not directly underneath. We'll give you the answers separate. So you can go through the questions, give them a go, and then give you the answers to check how you get on. Okay, and it covers everything through the book. Okay, so you won't get stuck with that. So I'll send Sanjeev those. So again, speaking about questions, by next Tuesday, which is your last day, the last part of that day, we'll just do lots of revision. Okay, we should finish book 2 by Tuesday morning at the very latest. All right, and that'll give you a bit of revision. Okay. Right, moving back on. So, as I said there, change engine speed, also very relative airflow, so affect angle of attack and on the fixed pitch propeller. Therefore, an increase in engine speed will increase angle of attack. In other words, the propeller is trying to go faster than the relative air. It's trying to escape the relative air, so it's going to increase your angle of attack. You slow the speed, angle of attack will decrease. Okay. You slow the aircraft, the angle of attack will also decrease. So there's a few things going on there. Increased engine speed means more power. That's good. The aircraft would accelerate and angle of attack would be restored to its original value. Okay. So give you food for thought. What sort of angle of attack do you think would be for takeoff? Do you think it'd be a big angle of attack or quite a small angle of attack for takeoff, do you think? But generally, it does vary, but generally, what do you think it would be? Small angle of attack or high angle of attack?
Small.
Yeah, small. We need the power of the engine. We don't need the forward speed yet because we haven't got forward speed. So we want an engine as fast as it can within limits to get as much torque. So we can get as much torque by making it like, if that's a blade, so it'll be like that, fine. So it's cutting through there nice and quickly. Once we get forward speed, then we can increase the, go that way, we can increase the angle of attack to grab more air once we've got forward speed. So to take off, quite a fine angle, get the forward speed, and then we'll change the angle of attack to an increased angle of attack. Good. So there we go, there we go. So forward speed, what I've got here is we've got RPM constants, the engine's at a certain speed, the forward speed has decreased. Okay, so therefore the angle of attack is increased because the forward speed of the aircraft has decreased. So in other words, the aircraft's fallen behind the relative airflow, so we can get a higher angle of attack. This is all at fixed engine speed. Okay. Now this time we're decreasing engine speed. So if we're decreasing engine speed with a constant forward speed, so the aircraft's flying at steady speed, but we've reduced the throttle. Don't worry about drag and stuff like that at the moment. So if we've reduced the engine speed, but the forward speed is constant, unfortunately, angle of attack decreases. Okay. The forward speed is trying to catch up the propeller. Similar though, we've got RPM constant and forward speed increased. So if the RPM is constant, forward speed increase, again, your angle of attack will decrease because the aircraft's going faster. It's trying to catch up with the relative airflow. And then finally, we've got RPM increase, we're going to get the engine going faster. We've also got the forward speed is constant. So if the RPM increased, the propeller is trying to escape the relative airflow. Okay, so 4 stages there. You want me to go through it again? Each one? We're happy? Yeah. Again, but we'll cover this again, don't worry. All right, so we'll move on a little bit. We'll look at what's called blade stations. Now, the propellers on an aircraft, they don't have these lines on. There is a line on there, we'll come to in a minute, but the lines represent a station, and the station is a certain distance per each station. Okay. So look at the blade route here. This is where the blade obviously joins the hub. And then in this example, if we have to draw a line every 6 inches up there, that's an individual station right to the tip. Okay. So you can see they're represented by 6 inches. There's your blade shank and so on. Also, by doing a cross section of the blade, you can see cross section of the blade gets thinner and thinner and thinner, and also the angle changes as well. So you can see by this representation here, the washout of the blade. But what we want to see here is we've got a total station here of 42 inches. Just an example, don't worry about the numbers. This is where your most effective point would be your 2/3 to 3/4. So let's have a look. Blade station designated distances along the blade measured from the centre of the hub or from some sort of reference line marked near the tip. Okay. And that one I've got there is the station measured from the centre of the hub in this case. As I said there, every 6 inches that is classed as a station. In this case, if it's divided into 6 inches, the 6-inch to 12-inch one is between the 12 and 18-inch stations. So what I've got here, the 6-inch and 12-inch one is between the 12 and 18 station. Okay, because that's the shank, we don't count that one. Okay, but these are split up into stations, and we use that for measurements, we use that for repairs and maintenance and that sort of thing as well. Now, division of the blade in sections separates the stations and provides a convenient way of discussing performance of the blade, locating blade markings, and finding the proper point for measuring the blade angle. Now, we call measuring the blade angle, we call it indexing. So remember, in the washout, the blades are twisted, so every part along that blade will have a specific angle, yeah, to maintain that uniform axial velocity. And locating what's called anti-glare areas. Okay, so a few things. That's why they're designated. So when you come to maintenance, you might find some damage on the blade. You'll say, station 4, I've got an indentation, I've got a crack, I've got a bit of damage. So that will go in your maintenance log, and you can actually fix it out. Then we've got a thing called master stations. Master station, it can be referred to as a reference point. It's a master station, that's where we take the reference from and stuff like that. It's measured in inches or millimeters, can be metric or imperial, doesn't matter, from the center of the hub. Okay, so master is from the center of the hub, the stations are maybe from the tip to the hub. Now, the distance to be measured to locate the master station is usually stated in your standard propeller maintenance manual. So obviously, for that specific propeller, go and find information, and you can find out where it is. However, you might find some blades have a little yellow line. I mean, I must confess, before I started doing these, I didn't know what the yellow line meant. I thought it was just for a visual indication that's spinning around. You can see the yellow line, but that is actually your master station. Right? You might have seen some of those already in some of the blades. So there's your standard blade, and then we just add on these little yellow lines onto the blade, and that is your master station. Okay, little yellow line. If the blade angle at the master station correct, then all blade angles should be correct if the blade has been carefully designed and accurately manufactured. That's for the engineers that design this to do that properly, and you there just to make sure as a reference point. So again, there's another example. There's a blade, aluminium blade, trailing edge, leading edge, and we'll just add on a little yellow line there. Okay, and that would be indicating your master station. If you go back to the graph that had the big loop on it, where it's most effective, that would be that point there. Okay, so next time out a propeller aircraft, you think, oh, that's what the yellow line is for. That's your master station. Okay. All right, moving on. We've got what's called power absorption. A propeller must absorb the power delivered by the engine. There's no point in putting a propeller in an engine, spin the engine, and it just goes flying off and it breaks. It's got to be suitable for that type of engine it's attached to. Otherwise, the thing's going to break. If engine brake horsepower exceeds propeller torque and propeller over speed, and both engine and propeller become inefficient, in other words, your aircraft's coming down. Okay. What do you mean by brake horsepower? What is brake horsepower? We've got shaft horsepower, brake horsepower, indicated horsepower. Oh, excuse me. What does anybody know what brake horsepower is? No. Probably hear about your fast cars and motorbikes. Oh, I've got 500 brake horsepower. You wish. Most cars maybe have 100 brake horsepower. You've got indicated horsepower. Now, indicated horsepower is the theoretical horsepower of that engine. In other words, it's an engine. It doesn't have a gearbox attached. It doesn't have a propeller. It's just the basic core engine. And when it comes off the manufacturer's engine bay, it will say that engine will give me 150 brake horsepower guaranteed. However, you attach a propeller, you attach a reduction gearbox, you get nothing for nothing. You might only end up with 100 horsepower, and that's your brake horsepower. It is your indicated horsepower, what in theory should be that engine power, minus everything that's attached to it. For your car, you'd be gearboxes, your rear wheel drive, front wheel drive, whatever it is, the power at the wheel. In our case, it's the power at the propeller. Okay, so brake horsepower is the parts you've taken off, the actual IHP indicated horsepower. Okay. Problem is most noticeable when climbing and high power and low forward speed. So if we'll recap, we want to highlight this one. If engine brake horsepower exceeds propeller torque, propeller over speed, which is not good. So the problem most noticeable when climbing at high power, low forward speed. If anything sounds like an exam question, that one sounds like an exam question. Okay, so worth making note of that one. Critical factor matching propeller to engine power is the tip velocity. Like I mentioned previously, we can't have the tip of the propeller going too fast because it'd be no use, and also ground clearance as well. So compressibility effects decrease thrust, drag, turbulence, reducing the efficiency of the blade. So we can't do that. So consideration imposes limitations on propeller diameter. So the actual distance of the blade, the length of the blade, how fast it can go, and the airspeed at which it goes. So in actual words, how fast the aircraft can go will also determine the type of blade. The bigger the blade, the heavier the blade, the more drag. So you don't put a massive blade on a small aircraft, and likewise don't put a tiny little blade on a very big aircraft. It's got to be proportional for the power and the aircraft it's designed for. The factors which may improve the ability of a propeller to absorb are as follows. Increase the blade angle. In other words, increase your angle of attack. That can absorb more power. Increase the diameter of the propeller. Yeah, make it wider, make it longer. Increase the camber of the blades. So the from the leading edge to the trailing edge, the actual size of the camber, the round part. Increase the chord length, the width of the blade. Yeah. So the distance from leading edge to trailing edge, we actually make the blade wider. So yeah, more air. However, downside to that, you make it longer, you make it bigger, you make it heavier. Or simply add another blade. So you can make that a 2, make it a 3, make it a 4. Again, pros and cons both ways. More blades, more power. More blades, heavier. Heavier, more fuel. So it's down to the designers to design the correct blades or blades for the engine. Okay. So like there, put more blades on there. So the usual method is to increase what's called the solidity of the propeller. And what I mean by, think of a propeller as spinning as a disc. A solid disc is obviously solid. A propeller is just a proportion of a solid disc. That's all it is. It's still a disc spinning around, but it's not a complete solid. You put more blades in there, you make it more solid. So hence why it's called solidity. So increasing solidity, I mentioned already, increasing the number of blades, increasing the chord of blades, and so on. Again, increasing the chord is easier. The lower aspect ratio of the blades makes it less efficient. Remember, go back to module 8, high aspect ratio, low aspect ratio. Design propeller with diameter, number of blades and shape is governed, again, by how much power you can absorb. And the propeller tip speed must not approach the speed of sound, or efficiency will be lost. I wouldn't worry about efficiency. If your propeller goes to speed of sound, it's going to break up. You'll get shock waves. Propellers do not like shock waves, and they will end up breaking up. Okay, so aircraft design is also a limiting factor. In other words, if you make a blade longer, okay, that's fine, but how big's your aircraft? What is your clearance from the tip of the blade to the ground? So if you make your blades longer, it might not last very long, yeah? So large diameter propellers may require the fitting of a longer undercarriage. Well, if you put a bigger undercarriage on, then that's going to make it heavier as well. So again, it comes to the design factors. So for maximum efficiency, the propeller must be able to absorb all the engine power available. Got a new student in the background there? Okay. Power can be absorbed by propeller design, but each method used has its limitations, obviously, and a compromise has to be made for the final propeller design. That's just a little table to just go in your books there. Look at the top there. Increasing blade angle, thrust, blah blah. Blade increased, speeds, propeller speed, increased tip speeds. Somebody's got a microphone on. Thank you. Altering the blade camber reduces aerodynamic efficiency, increasing blade chord, increasing weight, increasing turning loading. So there's pros and cons for everything. Increased number of blades, great. However, increased weight, structural difficulties, and stress in the propeller hub. Coaxial contra-rotating props, we'll come on to those. Basic contra-rotating props are two propellers on the same hub going opposite ways. Complicated, expensive, and a lot of maintenance there. Okay. Right, folks, what we'll do, we'll have a quick break now, and then we'll do a bit of recap, and then we'll go for my lunch with your tea. Because it's 11:30 here, so it must be near, I don't know, near 6 o'clock there. Okay, so just go for a 10-15 minute break. We'll come back in, a few questions, and then we'll recap some bits and pieces, and then we'll go for tea stroke lunch. Okay, so come back in about 15 minutes time, guys. Okay, see you in a bit. Your bottles of beer are massive, very big, very nice.
Yeah.
I mean, hopefully, I'll get back to Nepal at some point soon, and COVID goes away. Nasty that is. Okay. Right. Okay, let's go do some questions. Finish that one first, and leave that afterwards. Right. Wait there a minute. Okay, right. Where are they? Harim, Suraj, and who's that one? Kajendra, is that right? And
Khagendra.
number 16. What's your name again? Sorry.
M. Kumar.
M.
Yeah. Okay, right. Let's see what we've got. Go on, Sarab. All right. Let's ask you a question. If I increase the blade angle, what's going to happen? If I increase the blade angle, if I increase the blade angle without increasing RPM, what could potentially happen? So if the RPM is constant, just ticking over, but I increase the angle of attack of the blade angle, what could happen? What effect?
Stall.
Yeah, it could potentially stall, yeah. If you increase it to such a point past 15 degrees, that could stall. Also, it's going to put, there's the blade from fine to very coarse, a lot of pressure. That could potentially put too much torque in the engine and damage the engine good. How can we, hold on, I was going to say, if we increase the forward speed of an aircraft, let's go for Parasammy, apologise, I'll get your names yet, Parasammy. If we increase the forward speed of the aircraft without changing the engine speed,
Yes,
the pitch, what's going to happen to the angle of attack? Will it increase or decrease?
Forward speed increase and RPM also increase, sir. The angle of attack will increase.
Angle attack will increase.
Degrees, I think.
Decrease, yeah.
It is degrees.
Decrease.
Yeah. Because the aircraft's trying to catch up with the propeller, yeah? The aircraft's going faster, so the angle of attack between the relative airflow and propeller will decrease. So if the angle attack's less, then your blade is now almost in a fine position, so it can cut through the air nice and easy, which goes faster, which is good, a little bit, but too fast, we can overstress the engine. Good. Good. Okay. What would happen, Jonas, if I increase the speed of the engine? What would happen if I increase the speed of the engine, but not the speed?
Angle of attack will increase.
Angle of attack increases. I think.
Again?
Angle of attack will increase.
Yeah, angle of attack will increase, yeah. It's going to try and escape away from the relative airflow. Good. Good. That's fine there. What do we call the name of the blade as it travels through the air? The tip of the blade goes through the air, it's going forward. What do we call that angle as it's corkscrewing through the air? Sandeep? What do you think?
I think it's called a helical path, I think.
Yeah, helical path, yeah. So advanced air revolution, good. Helical path. As I say, most of this part should hopefully be nice and easy. It's just all modulate. There's nothing too different. It's pretty much the same. Just remember thrust instead of lift. We always get drag. We never get anything for drag. What was the purpose of the cuffs put onto the blade root on a propeller assembly? Anybody?
Improve the airflow around the blade roots.
Yeah, because you've got the hub assembly going relatively slower to the actual tip, which is going quite fast. Now again, depending on the design of the blade, determines how much vortices or turbulence from the tip blade. But likewise at the blade root, these aerodynamic cuffs that prevent turbulent air which could go down the intake of the engine and cause problems with the engine. So yeah, good. Good. What do we call, just a recap and modulate really, what do we call the line that goes from the leading edge to the trailing edge, the straight line?
Chord line.
Chord line?
Chord line.
What do we call the same sort of line that goes up and down like that? Again, from the leading edge to the trailing edge.
Camber line.
Camber line, good.
I mean,
Where would you find the master station? What would it look like?
Yellow line or something.
Yeah, your line. And roughly where would it be?
Roughly.
Where would you find the master station, roughly?
I guess on the blade tip.
Not on the blade tip. And it's measured from the blade tip. It's a measure from the hub.
Oh yeah.
Measure from the hub.
Measure from the hub, yeah. Roughly the same sort of position as the most effective point, which is roughly 2/3 to 3/4, yeah? Along the blade. Good. Good. Okay, right. Okay, the amount of thrust produced depends on several factors, which include 3 things. So the amount of thrust produced by propeller depends on 3 factors. Somebody give me one of them.
Angle of attack.
Angle of attack, that's one, good, yeah. Another one.
Diameter, chamber length.
Diameter will be there.
Yes.
Number of blades.
Number of blades.
Yeah, you could argue that, yeah. But more general than that, though. We've got angle of attack. What else can give us more lift or thrust in this case?
Question given, isn't it?
As a clue.
we didn't get the question. Can you repeat once more?
Yeah, more speed. And also the last one.
Diameter of propeller.
Yeah, you could do it. That one gives you more. Well, it gives you more blade, I suppose. Sort of like that is the shape of the airfoil. Yeah. So you've got angle of attack,
Yeah.
speed of the blades or the RPM of the engine, and the shape of the propeller as well. Yeah, you can see length as well. The more blade there is, the more it's going to give you thrust. Yeah. Okay, good. Right. So one I'm going to check is. Oh, we've covered that one. That's okay. Factors which may improve the ability of a propeller to absorb power. We've got 5 things there. So factors which may improve the ability of a propeller to absorb power are similar sort of things.
Number of blade.
Yeah, number of blades is one.
Diameter.
Diameter.
Camber.
Number, yeah.
Width of a blade.
Angle of attack.
Yeah.
Yeah.
Number of blades.
Yeah, done that one, yeah. And also the last one's the chord, yeah. The
Chord
width
length.
Yeah,
of the blade. Yeah.
Chord length.
So the high aspect, low aspect ratio type is good. Good. Right. Because what I want to do, that's not far off there. Covered that one. That's fine. Again, it's a nice, easy introduction. Well, hopefully a nice, easy introduction into propellers today. Nothing too hard at the moment. The main things to remember before we go for lunch or tea is the difference between forward speed, engine speed against the relative angle of attack. Yeah. So when we're taking off, we've got a very small angle of attack. So we've got high speed, high torque. So we take off, not very fast. But once the aircraft gets forward speed, then we can increase the angle of attack to guard more air because it can cope because the aircraft's going faster as well. Okay. And likewise, when the aircraft comes into land, they will also put it into a small angle of attack because that presents more of the blade to the airflow and it acts like a drag, a brake, an air brake as it comes into land. So lots of power, take off and landing. Once you're cruising, You just change it to a coarser blade, and it can just nice and easy stick over. Okay. Questions you might come across will be variations of an aircraft's going faster, what happens to attack, or you get increased RPM, what happens to attack. So if you decrease RPM and such like. So you could get a variation of any one of those 4 configurations in the exam. But again, I've spoken to Sanjeev. I'm going to send out some revision questions which cover the whole book. I'll send them this afternoon. So you have these questions for today, tomorrow, and over the weekend, so you can look over those. You can go further ahead if you want. That's not a problem, because we'll cover the ones we've covered each day that day, and then we'll recap the following day as well. Okay, we've only got 4 days to do this. Last time I was out in Nepal, we did the whole course in 3 days. That was quite compact. Okay, you've got an extra day because I've been online, but we will get through it quite quick. Okay, not too bad at all. And it's usually not bad exam either. Fingers crossed. Right. So, last one is what is the usual method to absorb power of the engine is to increase the solidity of the present. So, how can we increase solidity of the power? 2 main things. So, if we think of solidity as a solid disc, the propeller is part of that disc. So, to increase the solidity, what could we do? What do you think?
Increasing number of blades.
Yeah, we fill the gap. Yeah, that big round disc.
Or increasing the width.
Yeah, increasing the chord of the blades. Yeah, that is as well. Yeah, good. Good. Okay, that's about there for now. Let's see. Right. I think I won't go any further now. That's just a few questions I want to go through. The next section we're going to cover is we're going to go through solidity itself. We've got calculations, so we'll save the calculation to after lunch or your tea sort of thing. So we'll finish about 1:15. We'll finish now, and then we'll come back at 1:15 my time, which is that 7 o'clock your time? Is that right?
Yeah.
Thereabouts, yeah. Is that right? 1:15. Yeah, 6:15, 7 o'clock. So that'll be 7 o'clock your time. So 1:15 my time. We'll see you back about there. Okay, so a nice long lunch. Absorb what you've had this morning, and don't fall asleep in the afternoon. I appreciate it's late out there. Okay. So before we go, any questions from anybody about what's covered so far?
No, all good.
All good so far. All good students, yeah.
Yeah.
I'll have you for 4 days for this one, and there'll be a break, and I think you've got you for module 15, gas turbines, later on, hopefully if all well as well. Okay, so 17's a nice easy one to get into, and then 15's the deeper one. Okay, right guys, we shall see you in just over an hour's time. We're going to have a nice lunch, and revise if you want, or have a sleep, whichever you want to do it. Okay, and we'll see you in a little while. Okay? Bye for now. I think just got everybody back, I think. A couple of people missing, I think. I'm back for them. A couple of minutes. Hope you're all fed and water. Remember to put your cameras on, guys. Make sure you're alive and with us. Okay. Ready for part 2. Oh, Sandeep, you're not eating or drinking. What's wrong with you? I've got my cup of tea. I'm all right. I'm at you. Let's see. 8. Excuse me. Don't be shy, guys. Put your cameras on, please. Excuse me. Right, if you're back, guys, please put your camera on. That lets me know you're back in your room or wherever you are. There's one. Otherwise, you could just have logged on and gone to sleep. I don't blame you. I don't blame you.
Finishing up my desktop.
Could be a few more yet. Okay, we'll just get going. The rest of the catch up. Okay, so finished off there just before lunchtime with what was going to say, power absorption. Oh, message there, sorry. Message. Right, okay, back to that one. Yeah, just going through power absorption. Things we can do to get more power, but unfortunately the downside being there are the limitations, like increasing blade angle. That's great, but reduced thrust, torque, etc., blade length, yeah, more power, but again, size of a propeller, things like that as well. Okay, so let's move on. So I mentioned solidity before. So imagine a propeller is just one big round disc, and all we've done is cut into maybe 2 bits or 3 bits or 4 bits. So there's a space in between that disc now. So it's not a solid disc. So solidity is the ratio between the part of the propeller disc that when viewed from the front is solid and the part is just there. In other words, the spaces in between each propeller blade. If it was one big propeller blade, it would just be one big solid disc. So obviously it's not, we can't use that. So we look at how much or how many blades make up the solid part of the disc. The ratio is measured by adding the blade chords, the certain radius, usually at the master station. So again, use the master station as a reference point, and then we divide the sum of the circumference at the radius. We've a nice little formula just to keep you awake in the afternoon. A bit of maths in the afternoon, always a good thing. Okay, or maybe not. So let's have a look. The greater solidity, in other words, the more solid that disc is, as in more propellers, the less space it is, the greater the ability of the propeller to absorb power. In other words, it's more solid, as it pretty much sounds. It's less flexible. Now, solidity can be affected by increasing, like we saw before, the number of blades, as in contra-rotating propellers. Now, what we mean by contra-rotating is we've got one disc, maybe 2, 3 propellers, then directly behind that, we've got another disc, but going in the opposite direction. Okay, so contra-rotating means 2 sets of propellers on the same hub, or same axis, I should say, but one's going one way and the other's going the opposite way. And some specialist military aircraft definitely have them. Or increasing the chord of each blade, as is done with paddle blades. So let's have a look. There's the basic formula. Now, solidity equals the disk area divided by the blade area, and that gives you your ratio. So to work that out, we need to find circumference of the blade at the master station. So remember your yellow mark on the station, divided by the number of blades multiplied by the chord width. You go, oh my goodness, we've got calculations already. What on earth? This is a propeller class, not a maths class. Okay, we'll take the time this though. In the exam, you might or might not get it in the exam. It's one of those ones that might be, it might not be. We'll try and keep the numbers nice and easy though. Okay, so if you make a note or highlight in your page, in your book, the actual formula, and we'll look at an example. So let's have a look. It says that in practice with width of each blade, now this is a standard number they're going to use for any of the formulas. So in practice, the width of each blade at 7/10 or 0.7% of the radius, i.e. the master station, is multiplied by the number of blades and then it's divided by the circumference of the blade at master station. What's that all meaning? Well, let's put an example in. Just admit this person. So let's get it down on actual paper. So here's an example. If you got given a question, it says calculate the solidity of a 4-bladed propeller with a 10-foot diameter and a blade chord width at the master station of 1 foot. So the information you want to take from there is it's got 4 blades, it's a 10-foot diameter, and the blade chord is 1 foot. So let's put a diagram up in a minute. We need to calculate the radius first. Now the radius, using a standard number of 0.7. So 0.7 times the radius. Well, if it's given us the diameter, which is 10 feet, then the radius must just be 5 foot. So we can calculate something already. So the radius is simply the radius of the blade multiplied by 0.7 gives us 3.5. That's one answer we need first before we put into the rest of the equation. Okay, so you can see there, the 0.7 is taken from the centre to the master station area. That's where we get the 0.7 from. Now we've been told that the diameter is 10 feet. In other words, tip to tip. So we want to the radius. Well, the normal radius is just simply half that, which is 5 feet. But to do the full equation, we need to multiply by this 0.7, wherever the master station is. Hence the 0.7 multiplied by 5 feet gives us 3.5 feet. So that's one part. We need to make a note of that number, 3.5 feet so far. Okay, just let that sink in for a minute. So that's all we're doing first. We're just getting a number first before we put it in the whole formula. Okay. Moving on. So we've got our answer of 3.5 feet, or one part of the answer. We now put that 3.5 back into the formula. So 2 pi r, circumference of a circle, isn't it? Okay. Multiplied by 4, which is the number of blades. 1, 2, 3, 4. Okay, so 2 pi is simply 2 multiplied by pi, 3.14, that's standard. Multiplied by the radius, well, we worked out the radius, which was 3.5. So we work all that out, multiply by the number of blades, gives us 21.9. Then we round it up to make it nice, easy to count. 22 divided by 4 gives us a solidity ratio of 5.5 to 1 if we round the numbers up. Okay, so I'll just go back to the formula. So all we're doing is disk area over blade area. In other words, if the disk is solid, and it's the space between the disk and the blades, that's all with the ratio of how much solid parts are there to a complete disk. So circumference of the blade, 2 pi r, master station. The number of blades multiplied by the chord width. Okay, so we'll go back to that part. So we're going to work out the radius. The master station was at 1 foot. Nice easy number. Nice easy number to calculate. I'll say 1 feet. So there you go. There's your master station at 1 foot. Okay. Put it back in the formula. Well, we worked out the radius. So simply 2 pi r, 4 times the master station. So it's 4 blades multiplied by the distance of the master station, which is 1 feet. And then just round it up for easiness. Okay, and that's all we're doing. It's the ratio of how solid that disc is. Okay, the more blades, the bigger the number. Okay, that would make it almost close. All right. So a bit of an equation to start with, straight after lunch. Get your brains going. But again, in your books, you've got that. I think it's on page 37, if I remember right. Unless they've changed the books. Any numbers you can put. If we had 6 blades, 5 blades, obviously the more blades there are. If we had 6 blades there, then the ratio will be less, depending on the number as well. Because the more blades in there, the more solid that disc becomes. So then the ratio number would become smaller and smaller. If we just made that one bit of metal, then the ratio would just be 1 to 1. Obviously, no use for flying a plane, but it gives you an idea of how much more solid that disc would be. That's all we're doing there. We're calculating the solidity of the propeller. That's all that's doing. You might or might not get that in exam. Okay, worth making a note of the formula. And even if you want, put some numbers in there yourself. Maybe give yourself 2 propellers. Okay, if we only had 2 propellers there, then the ratio, the number would go up. Yeah, that would give us 2 into 22 be 11, so it'd be 11 to 1 ratio. So it's quite a small amount of material in there, just for example. So that's all it's doing. It's how solid is that disc. The more propellers, the more solid it is. That's all it's doing. Okay, we're now going to look at the positions of the blade in the hub and a few terminologies. At the top here, we've got flight fine pitch. That's the minimum working angle, in other words, a positive angle of attack. The blade is angled at to get some sort of thrust. Then we come down, we've got ground fine pitch. That's the minimum blade angle used for reducing torque for easier starting on turboprop aircraft, and also used for disc braking and landing. Now, it says on turboprop aircraft, some turboprop aircraft have a fixed turbine. You'll learn about this in Module 15 in a couple of weeks' time, and what's called a free turbine. Now, a free turbine is as it sounds. It is free. It is not mechanically coupled to the gearbox or the engine. It's only the gas that spins the turbine, which is connected to your propeller. Hence why it's called a free turbine. Now, for starting that type of engine, it doesn't matter if you're in the fine position or if you're in the feather position. It doesn't matter because it's not mechanically coupled to the engine. But some turboprops are what's called a fixed turbine. So the turbine, the shaft, and propeller are actually connected to the gearbox. So when your starter motor tries to turn the engine, it's got to turn the shaft, it's got to turn the turbine, it's got to turn the propeller. So that's a lot of stress. So to take the stress away from it on a fixed turbine turboprop, you put the blade angle into the fine position. So it's cutting through the air nice and easy. That takes the load of the stress of the starter motor. But again, we'll cover more of that in depth when we do Module 15. For the moment, just be aware of the positions. Then we've got coarse pitch. Well, coarse means large. So it's a maximum blade angle used for cruise position. Once you've got forward speed, remember, as the aircraft gets faster, the angle of attack gets less. So as long as we've got forward speed, we can increase the angle of attack or change the pitch of the propeller to a larger angle because it can cope. It's got that forward speed behind it. So it's like going up a gear in your car or motorbike. It takes the stress off it. We don't need the engine going really, really fast. And it's a fast speed. We can actually change the angle of attack to a coarser one. So it lets the engine take some stress off it. Feather position. Now, the way I remember, or you can use whichever analogy or way of remembering these. I always think it's fine position is fine face. Okay, going that way. Can't see my face, that's in the fine position. Feather, think anybody do darts? If you throw darts at a dartboard, some darts have feathers on, so the feather is in direction of the airflow. So that would be feather, that would be fine if you look at my face there. Okay, so fine cutting through the air sideways, feather into the airflow. Okay, the reason I'm going to feather position, if the engine shuts down, maybe emergency, or even on shutdown and landing, it will go automatically into the feather position. Okay, especially in the air, if an engine has a malfunction, it shuts down the air, we don't want the blade in a fine position like that because the wind will push on the blade and try and spin it. And that's called a thing called windmilling. And if that starts spinning a broken engine, there can be a lot of damage. So by putting the blade into a feather position, the air goes past it and stops the propeller spinning the engine. So that's what's called feather position. So feather is in line with the airflow, fine is against the airflow that way, sideways. And also, if an engine fails in flight and it stays in the fine position, well, you've got all that surface area going forward towards airflow. Well, that will act as a windbreak. That could potentially slow the aircraft down and actually bring the aircraft round, turn the aircraft unintentionally, which puts a lot of stress on the pilot. And obviously damage the engine. Next one down, we've got reverse pitch. It's just the complete opposite of normal pitch. We can reverse pitch, go from positive to negative. The engine still spins the same way, but this time, instead of pushing the air behind it, it's pushing the air forward, okay? So we're cutting the air a different way. That will give us reverse thrust, which helps slow the aircraft down, and indeed some aircraft can actually physically reverse the aircraft backwards and turn the aircraft around just by using reverse pitch. Flight range, when RPM has been selected at a constant speed, yeah, if it's a variable positioning propeller, that'll be the flight range, whichever's been preset. Transition range, that's just simply the change from ground operation to flight operation. We're transition from ground to flight to whichever range we want. And reverse pitch also goes into what's called beta range. Beta range is for reverse thrust range only available when the aircraft is on the ground. If you try to do that in air, one, it won't allow you, but two, if you did manage to do it, you would just rip the wing off. Okay, it'd be too much. And then we've got fine pitch, used for takeoff and high power climb. Very pretty much like the same one, flight fine pitch, that's just a really minimum positive angle, whereas the fine pitch is slightly more than the flight one. So if we go on to the diagrams now. So there's your ground fine pitch. You imagine that is spinning all the way around, hardly any angle of attack at all, okay? Hardly any at all. Fine pitch, you've got a positive angle of attack. So yeah, as it's spinning, it's trying to push air behind it, it's trying to give you thrust. Coarse pitch, very high angle of attack. Again, you would only use that once the aircraft's actually got forward speed. Feather, so imagine the airflow is coming from this way, so the airflow comes along, and it just goes over the airflow. So it will not try to spin the engine. And then reverse thrust, just like ground fine, it's gone below that. So as the aircraft, the engine spinning this way towards me, the air is now trying to push the air back that way, which pushes the aircraft back instead of forward. Okay, so normal position here, reverse position there. So as it's spinning towards me, that's going to cut through there and try and pull that propeller forward. But by going negative angle of attack, it's now going to push the air forward, which moves the aircraft back, okay, or act as a windbreak. So that's your main positions. Okay. Normally, if you're back here at AST, I would take it out in the hangar. We can show you some of these components and actually physically see them moving back and forward. I appreciate some of you are probably working on these already, so hopefully it's you know what I mean now. Okay, so just a few bits of terminology there. So we'll move on with feathering and windmilling. When an engine is stopped in flight, like I mentioned already, if there's in flight, the PCU, the propeller control unit, again we'll come on to that in a bit, maintains the selected RPM by reducing the blade angle. In other words, it fines it off. So it goes from quite a coarse angle to fine angle, so it can cut through, that's fine. Which is not so good. So the combination of a small blade angle, something that's coming out. So the combination of small blade angle and the forward speed of the aircraft produce a small negative angle of attack on the blades. All right. So what can happen is the airflow that's now going towards me will try and spin the propeller around. The engine isn't running, it's purely the wind pushing on the airfoil, which is giving airflow flow of the airfoil, which will try and rotate that propeller, which we don't want. We want it to be in the feather position, but if it's stuck in the fine position, the airflow can actually cause what's called a windmilling. Now we can use windmilling in good ways. We can use windmilling to start an engine in flight. You can point the nose down, get some forward speed. It will spin the engine, and using by the airflow going over the airfoil, we can start the engine up. But ideally, we don't want that normally. Negative angle of attack reverses the resultant force, and with it, the thrust and torque as well. So negative thrust, we've got negative thrust, you're increasing drag. We've not got positive thrust, but negative thrust. So that big surface area of the airfoil, which is trying to spin round, that's a lot of surface area, that's going to cause drag. That makes the aircraft difficult to handle, requiring extra power for the remaining engines. Now, if you've got two engines, you've got one engine and one wing, which is broken, and it's at a fine angle, and you've got one engine on the good side, well, this left-hand engine here is going to try and drag the aircraft round. So it's going to be a lot of stress and strain on the pilot, and indeed the aircraft. Negative torque causes the propeller to turn as before, but now the propeller is turning the engine, which can cause or increase damage to the engine. So the engine might be broken already, but if the propeller starts windmilling, there could be no oil in the engine now, and it could be you end up with a metal fire, internal metal fire, and then worse disintegration, and obviously the worst case scenario. So we don't want that. So to stop that, we put the engine in the feathering position. Now that can be manually done if it's a dual acting piston, or automatically by a single acting piston. What we mentioned before lunch there about a oil on one side of the piston with a spring on the other. You lose engine pressure, no oil means no pressure, so the spring takes over and it will physically push the propeller into the feather position, okay, on a single acting one. On a twin acting one, well, we can work that out as well. Windmilling will only happen if you've got forward speed. Okay, so if you're on the ground, nothing's going to happen. But if I push the aircraft forward without the engine rotating and it's in the fine position, then yes, you'll get excuse me, you will get windmilling action. So rotation of the propeller purely by the airflow going across the front of the propeller. That's what we call windmilling. Now we can have a windmill brake because you can be sat on the ground and no engine's rotating, but you don't want the propellers rotating either. So we can actually put a windmill brake in there, just like a car. So by allowing a non-reversing propeller to windmill, on landing it can provide an effective air brake as well. So just by using that, you can use it as an air brake. That helps slow the aircraft down in a controlled environment, obviously. On touching down, the propeller blades are turned to ground fine, which is just the minimum, as the engine is throttled back. So again, you get a small negative angle of attack produced in the blades, which provide you negative thrust and torque, and that will help slow it down. So we can actually use it to a good effect. The engine's working fine, we can put it to ground fine position, and we can use it basically as a wind brake. Have you all got motorbikes? Most of you got motorbikes? That was it there. All right. Some bikes have like 1000cc motorbikes, so you used to go around the race circuit. If you come to a very sharp corner, you would push up on your bike and use yourself as a wind brake. Well, by using the ground fine position of the propeller, you can use that as a wind brake, pretty much doing the same thing. Hey guys, the guys have just joined us recently. If you put your videos on, please, your cameras on. Right, so that's just an explanation or a diagram of what's actually happening now. There's your blade angle as normal. I'm getting negative torque because the airflow is pushing against it, so it's reversed angle of attack. Okay. So you get negative, still get a positive pressure, but on the opposite side of the blade. That's what it's saying. So when an engine stops in flight, the propeller would continue to turn to full speed. It will have two effects. This, obviously, it's going to increase the drag of the aircraft because you're now spinning the propeller. Well, the more it spins, the more drag it's going to cause. By hitting the propeller. Therefore, obviously, so it's a nice diagram. You can see here the blades in this propeller aircraft are all, there's a lead edges of each blade, all facing into the direction. So that's the feather position. So, excuse me, place the chord lines of the blades parallel relatively. In other words, in line with the airflow that's coming onto it. As mentioned, reduces drag, removes all thrust, lift if you back to aerodynamics from the blade airflow. So it will can potentially move around, but not very fast. It will just slowly move. It will only move if you turn the aircraft, yeah, because you get side airflow, side the pressure face there. But generally, we'll pretty much stay there. Reverse pitch, mentioned, used to provide very effective brake. So as we land, reverse pitch to set aircraft full speed, to reverse pitch angle. That can help us to select down. I said before, you can actually reverse the aircraft. If you select good is the Hercules aircraft, the Charlie 130, doesn't for a very quick landing. So in selection of reverse, propeller blades move to a negative blade angle, and that produces, strange enough, a negative angle of attack, and therefore a negative thrust. It just does the same thing as been before, but in the opposite direction. That's all it's doing. Reverse pitch, the torque will remain positive to oppose the engine driving the propeller. Thrust reverse will only take place if you must have your engine idle. Okay, so you've landed, bring your throttle back to idle because you physically can't select at any other point. Okay. Once it's idle and the aircraft's on the ground, wow. Anybody know what I mean by wow? Anybody know? W-O-W? Anybody got an idea of what that might stand for? So aircraft's on the ground, what's going to activate on the ground? Hopefully you should hook these already down. Well, weight on wheel. Okay, so it's a micro switch. When your undercarriage comes down, as the aircraft weight goes on the undercarriage, it will engage a micro switch. That will allow you to select reverse thrust and many other type of systems in the aircraft that are only activated or in fact disengaged when that switch is engaged. Okay, so it's a weight on wheel switch. And there is forward speed. There's no point in having reverse thrust if you're not going forward. If you're going backwards, unless you need to go further backwards, yes, you can reverse thrust. So you bring a throttle idle, there'll be a mechanical stop, push that back, go into your beta range, which is reverse thrust, and then you'll get your negative angle of attack to help that slow down as well. Again, no point in having reverse thrust at maximum power, because that'll just rip up. So there's just showing you a negative angle of attack. So your normal angle of attack would be off to this side, but now you've rotated the blade back the way, so that will change. So angle of attack is negative, thrust is negative. Your torque will always be positive. You've still got the engine, propeller trying to get away from the engine. So having that negative angle of attack will act as a windbreak. So there's a couple of moments we're going to look at now. We're going to look at centrifugal turning, and aerodynamic turning moments. Two different things that do two different ways. They are very similar. So CTM or centrifugal turning moment, or centrifugal force, back to physics, the force comes outwards. We've also got centripetal force, which goes, so we're only going to look at the centrifugal one, which goes outwards. Okay. So how's this going to affect the blades? Well, centrifugal turning or twisting moment, I'll probably abbreviate to CTM. Again, powerful force on propeller blades tries to turn the blades to a zero blade handle or very fine pitch. Purely by the weight of the blades spinning round, centrifugal force tries to turn it from a feather position, coarse position, to a very fine position. Okay? Purely by the centrifugal force.
Excuse me.
So there's no control there. If you spun the engine fast enough, with no control for the blades, it would just put to a fine pitch.
Excuse me.
okay for a little bit, but not for all time. So centrifugal turning moment, zero blade angle, very fine pitch.
Excuse me.
The magnitude or how much that CTM depends on the type of blade, the chord, the width of the blade, the weight, the RPM, and also any increase of any of those three will also increase your CTM. Yeah?
Sir, we got disturbance, sir.
Increase the weight of the blade. If you increase the RPM, you increase the so any of those you increase will give more momentum to the centrifugal force, which will then spin the propeller to a finer angle.
Hello, excuse me. Hello, excuse me.
Give it that so far.
Hello.
Excuse me. Hello.
CTM.
सुनेकै छैन सोल्टीले
त्यही त माइक अफ गर्नु भन्नु न सबलाई
भिडियोबाट भन्नु पर्यो हेलो हेलो कृष्ण विक्रम श्रेष्ठ हजुरको माइक अफ गर्नुहोस् त
So we don't.
Oh, bye.
Can you imagine if the centrifugal turning moment spins the propeller to a fine position? Well, what's going to happen to the speed? There's less resistance in the air, so the propeller is going to try and go faster. So we need to try and prevent that from happening. So there you go. So there's your heavy part here. So that centrifugal force is going to try and spin it, turn to fine position. So we need to control that. So we've got various types of systems we can use. We can use, earlier on, we've got the centrifugal weights. Again, we'll show you the diagram later on. Okay. Then we move on to ATM, or aerodynamic turning moment. Now, this is to do with the shape of the wing. Now, you put a wing in an air, the faster you move it, the faster it's going to get lift, especially if it's asymmetrical. Okay, and propeller blade is pretty much asymmetrical. But the aerodynamic turning moment, or ATM, it's slightly weaker force than the CTM, normally acting in opposition and trying to turn the chord this time to the coarse position. Okay, it's trying to fly away. It's trying to turn the blade from a fine position to a coarse position, purely because it's acting like a wing. The faster you spin it, the greater angle of attack you get, the greater the thrust, the greater the lift. So it's trying to turn it to a coarse position. So you've got CTM trying to go to a fine position, and you've got ATM to a coarse position. That's the easy way to remember it. ATM coarse, CTM fine. Okay. Blade center pressure is forward of the pitch change axis, just like a normal wing. And the moment of resultant forces turns the blade to that coarse pitch. In reverse pitch, the ATM force will turn the blade to a coarser negative blade angle. Obviously in reverse pitch, it's still acting the same way. Just because you've gone to reverse pitch on reverse thrust, well, you've still got an airfoil spinning, so the ATM will try and keep spinning it to a coarser position. ATM will act with the CTM to fine off the blades because it's counterbalancing each other, only when the propeller is windmilling. Okay, so these two forces, aerodynamic turn moment and centrifugal turn moment, will only fine the blades off when the propeller is windmilling. Otherwise, we'll do it individually. Okay. So there you go. There's your resultant forces, pitch change axis where the actual propeller is spinning. Your center of pressure will change slightly, and your angle of attack will change, I'll say, the same way. Normal position of thrust that way, or negative. I should change that round about, to be honest, and give you negative thrust. So there's your ATM. This time, different from coarse, it's now trying to make it a coarser pitch, whereas CTM was trying to make it a finer pitch. Purely because of the aerodynamics shape of that, the faster you go, the more relative airflow going into there, which will give you lift, in our case, thrust. So two forces doing two different versions. Another time they fine off together is when this is windmilling. Because remember, when windmilling, you've got air coming into that side Whereas when you're spinning the propeller, the engine, you've got the pressure side this side. Okay. And just a quick note, pitch change axis, the axis about the blade, which the blade turns when the blade angle is changed. So the pivot point, that's what we call it, the pivot point. So recap then on the forces, centrifugal force, so you've got your propeller spinning round. So as I said there, that's the force from the centre out the way, centrifugal force. Thrust bending force, if you look at the blue part here, that's your normal position of the blades, but due to the lift generated by the propeller, or the thrust, it tries to bend the blade forward, indicated by the green selection here. So the blades are actually bending pure because of the lift. There'll be more bend at the tip because that's a weaker point, okay? Because obviously near the middle it's quite solid, but as you get towards the tip of the blade, it gets thinner, slightly weaker, so the blade tips will actually try to bend forward as it's spinning around, so we call that the thrust bending force. In other words, the tips here will get more lift than here, there's more chance of them actually bending a little bit. So that's thrust bending force. And then the torque bending force is obviously the blue is represented by the blade itself, but the fact that the blade is actually trying to bend off the hub a little bit, that's the torque. So the centre will be going slightly faster than the tip. So in effect, again, the blade is trying to bend slightly. Okay, just like a golf club. Anybody do golf? If you golf and you throw a golf club, the golf club actually bends a bit, doesn't it, before it hits the ball? It doesn't stay straight all the way down. If you watch it in slow motion, you'll see the golf club bending before it hits the ball. The propeller is doing the same thing. Very, very marginally, but it is trying to do it. All depending on the power of the engine as well. Then we've got the torque bending force. Okay, and that's the torsion of the blade on the actual hub. Okay, torque, twisting motion. Excuse me. Okay. Now, thrust and torque produced by the conventional propeller engine. Okay, a thrust from your lift from the propeller blade, and the torque by the rotary motion of your engine. And that's a measure of how much force is acting on the propeller, cause it to rotate and move the aircraft forward. Yeah. So the more thrust, the more torque, the faster your aircraft will go forward. Now, thrust is a result of the aerodynamic forces at the propeller blade. Like we said before in aerodynamics, that we call the thrust lift. But in our case, for propellers, we call that thrust. Okay. Torque, again, a resultant force against the power and RPM of the engine. Okay, depending on how powerful the engine is, the greater the power, the greater the torque. Now, the distance from the pivot point to the point where the force acts, we call that the moment arm. Going back to module 2 in physics, we're about turning moments, counterclockwise and clockwise. Well, the moment arm is the pivot point. Same sort of thing, torque, when you go and get a torque wrench, you go and tighten a bolt down, use a torque wrench. Your pivot point, or the fulcrum, sometimes you call it fulcrum, is that point where you're turning your torque wrench on your bolt. Okay, same thing for propeller. The greater the torque. The moment of a force, or the relative airflow, about the pivot point is what known as the measure of the force's tendency to produce torsion and rotation about the axis. So as well as rotating, we're also getting the torsion as well, hence the torque. This is equal to the vector product of the engine power RPM, of the radius vector, which is the moment arm, from the axis of rotation of the point of the application of your RAF, your relative airflow, and the force vector engine RPM. So a lot of stuff going on there. So what does it mean? Well, there's the diagram here, engine power and direction rotation, you've got going that way. You've got the relative air force going that way, so you're getting torsion, you're getting the twisting moment. Then you've also got the moment arms, okay, and your pivot point, which will be your fulcrum there. So you've got forces going that way, forces going that way, which will give you the torque, okay, and then the thrust going forward. And it's also defined as a turning or twisting force. So in order to convert engine power to thrust, an engine requires a propeller, otherwise we can't go forward. The thrust obtained by accelerating air mass. So we need to grab that air in front of the propeller, push it back away, and the reaction to acceleration rearwards will then therefore move the aircraft forward. Newton's third law, heavy action, opposite reaction. So the propeller's going forward, the air's going backward, pulls the aircraft forward. Newton's third law. So looking at two different types. We've got a propeller system which has a large mass of air, so it grabs a lot of air, but it's quite a small acceleration. Okay, you think, oh, that's not very good. Okay. So the little propeller aircraft there. So a large mass of air, we cut through it, we push it behind the aircraft, and that gives us, well, a slow amount of velocity, a slow amount of speed. In a jet engine, we do the opposite. We take generally a small mass of air, we get a far larger acceleration. So small mass of air in the front, large mass of air at the back end. Okay, so slightly different. So two different methods, does the same job, but one does it faster than the other one. So hence why I'm using turboprops or propeller aircraft at low altitudes, and we tend to use jet engines at higher altitudes. Okay, so propeller, large mass, small acceleration. Jet gas turbine engine, small mass, large acceleration. And you'll see the exact same one again in module 15. So no expense spared graphics. 3, 2, 1, go. Okay. So I just explained large mass, small acceleration, small mass, large acceleration. The propeller system therefore uses less kinetic energy than a pure jet engine to achieve a given thrust. Due to the limitation of propeller, the propeller speed, affecting tip speeds, we don't want the tip speeds going supersonic. The propeller-driven aircraft is far better suited for low level and lower speeds. It can cope at lower speeds. Yeah, that's sometimes when you see some fly past, some aircraft doing a fly past, maybe the propeller aircraft, they're fine, and the jet engine aircraft are trying to go slow, but they don't like going slow. They like fast speed. So faster, higher levels is jet engines, lower levels, low speeds, propellers. As I said before, thrust, the component acting at right angles to the plane of rotation. So the propeller spinning around, the lift we're getting from the propeller provides the thrust. Torque I mentioned already, component acting on the plane of rotation, opposing engine power, torque and resistance offered by the propeller. Negative torque, just a bit of recap, occurs when angle of attack becomes negative, which tends to drive the propeller. The airflow touching onto the propeller or negative angle of attack will give us negative torque. So, factors affecting thrust and torque. Well, definitely air density. Oh, yeah. If we were able to get a propeller aircraft at 30,000 feet, not that it wouldn't, what happens at altitude? Air density gets less. There's less air. There's less air for the propeller to grab onto, so it would have to work really, really, really hard to get the same amount of large mass air to get that forward speed. It just can't do it. Hence why the jet engine is far better. So increased air density will increase thrust, which is nice thick air. So again, where do we find the thick air? Low level. But at the same time, dense air offers greater resistance. So we've got a trade-off. Yes, we've got more air, but it also is thicker, so it's harder to get through. So we need more torque. We need more torque, we need more engine power. Angle of attack, yeah, I saw before. Increasing angle of attack will produce more thrust because we're increasing the lift of the propeller. And torque up to the stalling angle of about 15 degrees, just the same as a wing. So therefore, the optimum angle of attack will give the best thrust-torque ratio. All dependent on the airfoil itself, again, 2 to 4 degrees. And again, propeller speed, or your RPM, thrust and torque will alter directly with the speed of rotation. You increase the speed of engine, you spin the propeller faster, well, that's going to increase more lift, as we know is thrust. Okay, so we get more power. It will also increase more torque. You've got the resistance to the engine there. Now, the total torque force on propeller blades will cause a turning moment, or torque, just like in physics. That opposes the engine torque and also tends to rotate the complete aircraft in the opposite direction to that in which the propeller is revolving. So we've got the torque of the engine spinning propeller. Now the opposite of that, Newton's third law again, that engine is now trying to spin the aircraft the opposite direction. Okay, so that can affect certain conditions. Imagine a helicopter. Helicopter's got a big propeller or a rotor on the top. Well, without a tail rotor, the engine would spin the helicopter one way as it spins the rotor the other way. Hence why if a helicopter loses a tail rotor, it loses control and just starts spinning out of the way. Aircraft are not as bad, but they can try and spin the aircraft, especially on the ground. Propellers are revolving at a steady number of revolutions per minute, and propeller torque and engine torque will be exactly equal and opposite in an ideal scenario. So it should stop that twisting moment. If the propeller rotates in an anti-clockwise, if you're in the cockpit, you look at the propeller, it's going an anti-clockwise rotation. The torque reaction will tend to rotate the aircraft in the opposite direction. In other words, it will make the aircraft roll to starboard, okay, or to the right-hand side. So if you look in the cockpit, the propeller spinning around anti-clockwise, then the aircraft will roll the opposite direction. So one method to counteract that involves the use of washout. Like we saw before, your wing angle incidence. Exact same propeller, wash out the twisting of the wing on the lift and the wing. The difference in lift will cause a rolling motion, causing the opposite reaction. And that will count. Again, that's down to the designers of the aircraft, propellers, the engineers, the design the stuff to balance all this out so the aircraft just flies straight and level. Okay, we're just the ones that fix it when it goes wrong. So the rolling motion caused by torque is also counteracted by the main undercarriage. So when you're on the ground, yes, you're great, you've got the wheels there, so the wheels can stop it doing it as well. That results in more weight being supported on the starboard undercarriage. So in the air, the aircraft's trying to turn to starboard. And on the ground, it's trying to push down on the wheel, if that makes sense. So the undercarriage in this case is having an equal and opposite reaction to support it. Now, this increases the rolling resistance on the starboard undercarriage, which causes the aircraft to swing to the right until the wings take the weight on the undercarriage. You might have seen this, some cars, some big powerful cars. If you watch it, they rev the engine very quickly, you can see the bodywork giving a bit of this, yeah? Just depending if it's an inline V8 or V12, you can see that trying to roll the body. It's the same effect with an aircraft. So torque effect in the aircraft. Look at this one. We've got torque reaction, increased rolling resistance on the wheel. So yes, you've got airflow going over, but you've got more torque on one side than the other one. Such like. Okay, so let's just show a different example. Now, before we go too far ahead, let's see where we are. Yeah. That'll do for there. Okay, I think that's a good point there to stop for another break, because we're going to speak about torque meters and type systems and what they're used in. Okay, so I think we'll stop for a break now. What time on? 10 past. Yeah, come back at 2:30. So 2:30 my time. I'll get used to your times. So it'll be 2:30. It'll be 8:15. Is that right, your time? And we'll see you in a minute. Okay. So back at 2:30, guys. Right. Oh, 10. Good, 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 good. All right. 10 is good. All right, guys, have just joined in. Please put your cameras on. All right, I need your cameras on, guys. Keep them on as well. Okay. I know it's getting late out there for you guys. It's still mid-afternoon for me, but I know I appreciate it's getting late in the day for you. You'll get to your bed shortly. Or you're going back to work. I don't know, one of the two. Anybody do night shift? I hope not. Good, keep them on. That's fine. Saraj, Arim, Puspa. Okay. All right. So that was torque. Chatting about torque earlier on there. What I'm trying to do at the moment is get as far as possible. We're an easier day tomorrow. We'll probably finish book 1 tomorrow and possibly start part 2 tomorrow as well. The reason being is the time we get to Monday, we want to be quite ahead of the game. So by Tuesday, lunchtime at the latest, you're pretty much done all the theory, and I'll just leave for a couple hours in the afternoon. It's just lots of revision. Okay, as many questions I can give you. I've sent Sanjeev off revision questions. There will be some answers at the bottom of those. So try the questions first in your own time. It goes through the whole book, all the sections. Again, so Sanjeev will send them out to you, or you can collect them from him, whichever is easiest. And that'll help you with your revision on the book as well. Okay. So let's move forward. I'm going to start speaking about torque meters. Get onto the right bit first. All right. Now, if you've done module 15 first, we've really covered torque meters already. But so going back, we'll do torque meters, and then you'll speak about torque meters again in 15. And it's the exact same system, same sort of systems we're looking at. Now, we need torque meters because obviously with your engine spinning, the propeller, you're producing torque. Depending on the angle of the tack of the propeller blade will determine how much torque there is, and also the forward speed of the aircraft determines how much angle of attack. All relating to how much twisting motion is going between the propeller and the engine. So it's very crucial. We need to, right, you've got one, all your cameras gone off. I said keep your cameras on. I know you want to go home. You're stuck with me for an hour or so yet. So torque meters, we need to monitor. There'll be a torque meter gauge in your cockpit, electrical, digital, analog, whichever version it is. We need to monitor how much torque is being, in other words, the stress in the engine, so we don't damage the engine. Okay. So propeller torque is usually measured with torque meters of some variety, which are normally located on the reduction gearbox on propeller shaft. Now, apart from very, very small piston engines that have the propeller straight on the shaft, most of the bigger engines will have a reduction gearbox, because if we put a propeller bolt onto the shaft of the engine, the crankshaft, well, that engine's going to be going very, very fast, a lot faster than the propeller can handle. So we tend to have a reduction gearbox in there, which, although the engine's going very fast, it's not spinning the propeller as fast. Okay, we need to reduce it, just like a push bike or a motorbike. You have your crank sprocket and you have your wheel sprocket. Okay, takes a bit of torque out of it, so we can have more torque but less effort on the actual propeller, which is good, but we need to maintain the type of torque we're using. So requirements is to provide an indication of the power to a cockpit gauge, and we will look at what's called the water methanol system. Now, the water methanol system is just a boost for the engine. We actually inject a water methanol mixture into the engine to give it more bang. Okay. Also, we help it if it's, especially like in Nepal, very, very hot climate, lots of hot air, so it's a lot less oxygen. So some aircraft might need this injection system to help them actually get off the ground. Here in Scotland, very cold, very cold air means we very dense air. We don't tend to use that water methanol, or we don't need it here anyway. But certainly for hot climates, longer runways, whatever, water methanol can assist the power of the engine. We'll go more into water methanol when we do module 15. And the requirement is just the automatic feathering system as well. So we need to know the torque that's going on of those systems. So we need a copper gauge, something for the water methanol system, and automatic feathering system too. Same for module 15, so this will help for module 15 as well. There are basically two types, nice and straightforward. You've got what's called a hydromechanical, so a fluid mechanical type system, and strange enough, an electrical system. Okay, electrically operated system. We'll look at the two main types. So it's the two ones to remember: hydromechanical and electrical. So starting off with the hydromechanical one, the fluid we're going to use is engine oil. It's not a gearbox oil as such like a car, but it's purely engine oil. And it uses engine oil which is compressed between two opposing forces. And we'll look at that. So the resulting pressure is sensed and indicated on a gauge and is in direct proportion to the torque applied. So what the gauge is reading, that's how much pressure is in that system. Yeah, you squeeze something, you increase pressure. And all that's happening is that propeller in the mechanical one is trying to escape off the shaft of the engine, but it's reacting against some pressure pads. And the more pressure it puts on those pads, the more it squeezes the oil, which goes to the gauge and gives you an indication of the cockpit. Nice straightforward one. We'll have a spur gear type that uses resistance to rotation in a single plane of rotation and what's called a radial axis, so rotating round an axis. Yeah, and this is what we've got. This is a very, very basic. Somebody else coming in. Come on. So what we've got in your cockpit, you'll have an indicator. We'll need some sort of pump to pump the fluid to the system. You'll have a piston at one end and a piston at the opposite end within the system. Now, these pistons will move to increase or decrease pressure depending on how fast your engine is rotating in relation to the propeller. Now, the middle part here is your crankshaft. Okay, that's the actual engine shaft itself. We call that the sun gear. The little ones here, these are the planet gears, just like a solar system. The planet's going around the sun. And then around your stationary gear, which doesn't rotate at all, that'd be like your annulus or fixed gear. Now, as you can see here, the crankshaft's rotating around that way. Well, imagine these have got gears on them. So you have spur gear there and the gears on the little ones. So as this is rotating round, it's going to try and rotate these planet gears that way. So this one will go that way and that one will go that way. Now, if it's a medium power, they're just going to rotate around and not do too much. But the more resistance to torque, because this part here will be connected to your propeller. So the more resistance, the more this outside stationary part will try and twist. Okay, so if it's nice and easy, it'll just stay where it is. But the faster you put the engine, the more resistance on the propeller, depending which direction it is, will twist this whole stationary gear. Well, if that twists, certainly in this direction, the way it's going with the crankcase, that will push fluid up, which will increase pressure, because pressure is resistance to flow. Okay, and likewise here, that's going to put pressure down as well. So the faster that's going, the more it's going to try and rotate this fixed gear, which will move the pistons up and down according to how much torque is there. Dead simple scenario, and obviously the torque indicated is proportional to the speed. Okay, a very basic, simple, using planet gears, spur gear, sorry. So the crankshaft rotating round, which tries to rotate these spur gears, planet gears, around the stationary one. Okay, nice, straight and easy forward. I will try and get it animated at some point. It just takes a bit of time to get going. Okay, so you can see what's going on there. Rotating clockwise, these planet gears will start to move around, and as they move around, the faster they move around, we'll try and move this station one in the opposite direction. Okay, purely by the mechanism of the gears. All right. In that sort of glorified version, the diagram before is a simplistic version of this one. Same again. There's your propeller shaft. So the propeller would be attached to this point here. That is attached to a reduction gearing. The reduction gearing is then attached to the crankshaft. So the engine would be back here somewhere. The crankshaft going to the reduction gearbox, these ones here. So the engine will spin really, really fast, but the reduction gearing reduces that speed, provides more torque, which propels the propeller. As you can see in there, you've got these planet gears which go round the helical gearing. On the ends there, you'll see the torque meter piston. So the piston there will push against something because the propeller's trying to slide that off, that shaft. So as it brings us forward towards the propeller, it will push that piston. That will increase the pressure in the system, which will then increase your gauge as well. Okay. So it's a reaction against the pistons. The more power, the more thrust, the more it's pushing that piston onto the end and squeezing it, which will increase your indication in the cockpit. So a couple of different mechanical versions there. There's a whole diagram, but you're not expected to remember the whole thing. This just highlights what's actually going on. You've got engine oil, you've got a torque meter pump to provide the oil supply, and then you've got oil to the lay shafts, the left-hand side, whatever, cockpit gauge. The distance between the sensors, the greater the indication in the cockpit. So either a speeding one or a fixed one which twists. And that will be amplified through an amplifier to give you signal onto your gauge. So this is the principle of the twist one. So you've got two phonic wheels on the shaft, okay? You'll have one for propeller and one actual shaft. Now, the blues and the greens here, they just represent teeth. So there's the teeth, okay? There's your two sensors. So the greater the twist, the greater the angle. So at the moment, that's about there. So these two shafts twist, that makes a bigger angle, which makes a bigger signal, which will give a bigger indication on your cockpit gauge. And that's the electrical torque system. Very, very similar you'll find in gas turbine engines, module 15, you'll find something very similar. We'll look at that. So here's another version of the same thing. Two shafts, you've got a propeller shaft and you've got engine shaft. Obviously they'll be engaging at the same time, but if the propeller shaft decides to go a bit faster, or likewise the crankshaft goes a bit faster, depending on the angle of the tank and propeller, there'll be an increased gap or a decreased gap, depending. Now again, depending on the setup, you can see the red gap there. Okay, so the difference between the gap on in case of Y and X will decrease or increase it, depending the gap that's available. Okay, so all it's doing is the difference between the distance of the X and Y in this case will give a greater or less signal frequency to the amplifier, which will give a signal to your cockpit. Okay, it's just a slightly different version of the same thing. We need some reference pressures though. So for a given power torque meter, oil pressure differs with engines. So therefore, necessary obviously to establish a reference figure for each engine on a test bed after new build and overhaul. So when you get an engine, rebuild an engine, you put in what's called a test bed. As it sounds, you can test this engine test bed. I used to do that for the gas turbine engines myself as well. And you'll get a reference figure. You'll pretty much test this engine to the point of destruction. Then you'll bring it back to the normal level. So when you problems. So if you suspect your engine's not as healthy as it was, you check the figures with the engine logbook, you check your actual running figures in the cockpit, and then compare, and there should be a slight discrepancy, and hopefully within tolerance. Obviously, engines will wear out, like everything else, getting older, just like myself, wear out, and you need to be refurbished. Okay, be allowed up to a certain amount of discrepancy. So yeah, now what we've got here is you'll have dry figures, and that means what means dry is without